respect to the introduction, followed with what is TCAD and why there is a need for TCAD and why we go for preferring a physics-based modeling, followed with the overview of Silvaco TCAD to sign-off flow, and getting exposure with several Silvaco products, that is, which includes the process simulator, device simulator, and other interactive tools that is included in Silvaco. And a few applications from the perspective of optoelectronic and power device simulation will also be projected during this presentation and followed with this summary. Once after this presentation is done, we'll be going for a break and we'll be continuing with the process demonstration of the process simulator. So without any delay, let me move on with the introduction. Technological advances in the past few decades have taken place at a breakneck pace. So from the new device to new technology, which includes like Apple iPad and 3D TV, we have new ideas that continue to change our daily lives. To keep the semiconductor industry on its so that is the So from the new device to new technology like Apple iPad and 3D device, we have new ideas which continues to change our daily lives, and the innovation is not showing any sign of slowing down. So these new products are only made possible by matching the innovation in semiconductor technology. So this particular this makes the semiconductor industry to be one of the key driving force in today's global economy. Obviously, the structure of the transistors now switch from the planar to vertical design in order to keep the semiconductor industry on its technological growth track. Heavy emphasis has been placed on the technology computer aided design, that is TCAD tool, for achieving a key long-term research results. So with this basic introduction about why there is why people in the semiconductor industry, how do they manage by means of using TCAD for achieving their research results, we'll get into understanding, detailed understanding of what is TCAD. So TCAD refers to the development and optimization of semiconductor processing technology and devices. TCAD is a software modeling of actual semiconductor fabrication processes as well as physics-based simulation of the operation of semiconductor devices. So TCAD has the potential in order to perform the semiconductor device design, manufacturing process design, circuit design technology, and then some manufacturing efficiency optimization, process control, mainly due to their advantage of solving the fundamental and complex partial equation, like which may include a diffusion and transport equation. So with this physical approach, TCAD provides predictive exactness for a wide range of technologies. The TCAD simulations are therefore used in the development and characterization of new device systems in order to majorly to reduce the expense and time-consuming test wafer runs. So with this overview of what is TCAD, let us understand why there is a need for TCAD in the semiconductor industry. Majorly due to these 5 reasons that's been listed over here. The first one being the reduced development cost. It is TCAD helps us to reduce the time and manufacturing cycles that is being spent in order to develop a semiconductor technology. So our ITRS roadmap indicates that TCAD simulation can reduce the cost during the development cycle by approximately of 30%. And then we have visualization of internal physical processes. Using simulation, we can understand what is happening inside the device. Like for example, when you take an experimental measurements, it will let us know what happens, but not why it happens. Whereas TCAD can provide the answer for all the why questions. So that's the reason which we say visualization of internal physical processes. And then moving on with design technology co-optimization, which is shortly called as DTCO. TCAD is a part of DTC workflow. That is, it improves designs across multiple domains, which may include a layout, process, device, or spice, and even RC extraction. So a full TCAD to spice flow in an integrated DTC, that is design technology co-optimization, that is environment delivers a clear, actionable results for circuit design optimization. Followed with, we have virtual experimentation. So virtual experimentation, I can categorize it into the first one being the experiment with a cause and effect. That is, when we, as a user, we want to change the device design, for example, a layout, or the technology, that is semiconductor process steps, or the device operation condition like biasing, etc. So we can easily understand and improve the device performance. That's the reason we say we have the experiment with cause and effect. The next category in virtual experimentation is about experiment with theories in TCAD. That is, the TCAD provides the control on the impact of various physics in the device via a model settings and coefficients. So if theory is applied to simulation, when suppose if it matches with the measured result, obviously we have found the root cause and gained some physical understanding of device performance. And the last being the communicate device complexities clearly. Semiconductor device design and processing of semiconductor is a complex task. So engineers must work collaboratively in order to solve problems, explain issues, and opportunities to a variety of colleagues with a varied technical expertise. So utilizing TCAD, we can clearly communicate device and process changes, communicating the potential performance improvements with a clarity, obviously considering that is without compromising with the manufacturing cycle time. So minimizing the manufacturing cycle time. So all these advantages have attracted the researchers to use TCAD globally. So with this detailed explanation about what is TCAD and why there is a need for TCAD, let us quickly move on with the understanding about the design for various technology sectors. Physical design plays a crucial role in a variety of technology sectors. So as we could see here in Silvaco, we have categorized the application into 5, which includes the display, power, reliability point of view, optical simulations, and advanced process development devices. So under the display, let me take an example of thin film transistor technology. So Silvaco TCAD and SPICE tools, they contain a comprehensive set of models that are designed specifically to take account of the poor electrical performance of thin film transistor, generally if it is manufactured on any non-crystalline silicon substrates. Then while considering power, Silvaco's process and device simulation, they have all the ingredients. Like I can say that is state of art from the mesh, solvers, everything that are like essential to accurately simulate these type of power devices in both 2D and 3D perspective. And then reliability and radiation, that is Silvaco advanced model for reliability and radiation effects. They allow the device and circuit performance in order to be optimized for a lifetime and a robustness enhancement. The next category is about optical. Considering optical optoelectronic simulations, we'll be definitely in the future slides, we'll be discussing in detail about these devices. Just a few words about it. Silvaco tools incorporate the electrical and optical physics that is required to simulate a wide range of optoelectronic device types and materials. And then we have the last category, that is advanced process development. So the novel devices, I can say in simple terms, like the novel devices or any complex structure based devices comes under the category of advanced process development. So in for example, in order to simulate a challenging new technology, then Silvaco support with all these novel devices which works with a different mechanism and provide us with a great accuracy in the results uptime. So with this introduction about the various applications that is possible made by Silvaco, let me just quickly move on to the next. Okay, why use physics-based modeling? So majorly for three different reasons. So the one is going to be the predictiveness. Another, Silvaco, that is TCAD, provides an insight about the tool, and then it captures and visualizes the theoretical knowledge. So physically based simulation, it provides us insight and encapsulates the fundamental phenomena, and it provides information which even is found to be very difficult or even very impossible to measure. So this is why we require physics-based modeling. And then moving on further, Silvaco, leading EDA provider. And okay, a few words about Silvaco before we get into detail about the products that are being provided by Silvaco. Silvaco is a leading electronic design automation software and service provider, which was founded in 1984. And Silvaco delivers a full TCAD to sign-off flow for vertical markets, which includes the display, power electronics, optical devices, radiation, and software reliability, analog design, memory design, advanced CMOS devices, and intellectual property development. So for over more than 30 years, Silvaco has enabled its customer to bring the superior products to market in a very shortest time with reduced cost. So semiconductor fabs and design houses, from around the globe, they rely on this Silvaco's expertise in order to help to develop the technology behind the chip. So Silvaco mission is majorly to help the customers accelerate the pace of technological innovation and their time to market, while also having in mind reducing their cost in developing the next generation chips. Moving on further, Silvaco providing capability across all nodes. So this is quite right now aware for many, what are the capabilities and what are the technological nodes is Silvaco working with. So it has reached 5 nanometer and even below, and we are working in atomistic level simulation as well. We have a dedicated tool for performing simulation in atomic level. And moving on further, Silvaco DNA. DNA is the core is going to be TCAD, which is going to be the market leader in the semiconductor industry, and number one TCAD, Silvaco TCAD is number one for display market, and it's ranked number one for radiation and soft error reliability. The next shell formed in Silvaco DNA is about the EDA for transition level design. So SPICE connects the physical and the electrical world. So full custom design flow for major nodes. And this particular EDA tool of Silvaco is providing us with the best parasitic reduction tool and providing us with the best variation analysis tool for high sigma. And the next shell is formed by the large portfolio of intellectual property. So we have a standard cell library foundation and large automotive IP portfolio. So with this, let us quickly move on with understanding about Silvaco, overview of Silvaco TCAD to sign off. Yeah. So for the first and the predominant one is about the TCAD. So where a structure is being undergone with various fabrication steps using the process simulator, and then it is being characterized several parameters, which includes DC analysis or AC analysis, transient analysis. Everything is being characterized using a device simulator. And in many cases, single device is not we actually want to work. So we want to work for many devices that are being tied together. Then we need to move on to the next level. That's what we call it as SPICE modeling. So Silvaco Smart SPICE, in this case, the PDKN modeling. It is a high performance parallel SPICE simulator that delivers the industry leading accuracy. It is proven that a comprehensive solution for applications, including the simulation of a complex high precision analog and mixed signal circuits, memory, custom digital design, and characterizing cell libraries of advanced semiconductor processors. So this Silvaco SPICE modeling technique, it uses an intelligent architecture that is developing a multiple solvers, stepping algorithm, and computation technique. So the result is going to be very accurate, robust convergence, and industry-leading performance and capacity. Next, moving on with we have design and verification. We have several tools that is included in Silvaco, where we have a completely dedicated tool that is Gateway, which is going to be a schematic editor. And then we have to perform that is layout versus schematic, and to perform the design rule check, we have the Guardian tool. And for parasitic extraction, we have Hypex. And for if it is 3D, then we have Clever. And parasitic reduction, we have Jibaro. And apart from that, for layout designing, we have a specific tool that is Expert. And coming to the simulation, the last step, it is simulation and analysis. So that is high sigma analysis for example, I can say CMOS image sensor control, or a fast Monte Carlo analysis that is to save the simulation runtime, or local mismatch analysis for ADC, or statistical corners for quick design iteration. Everything are possible by means of using a tool called Varman in Silvaco. And then from the reliability point of view, we have it is a block to full chip level analysis. And then for early that is early layout of electromagnetic analysis, or SPICE accuracy, we have INVAR. And yeah. So with this quick introduction about Silvaco TCAD to sign off flow, we'll just move on with the sources, available sources for Silvaco software users. Silvaco provides various sources to its users. So it allows for Silvaco TCAD tool allows for an advanced interactive GUI based tools, and it provides a design space exploration. That is, if a client if a user would like to perform a design of experiments, or would like to go for an optimization of a particular parameter, yes, the space is being provided where a user can provide the parameter and go for experimenting this. Next is about like a number of work standard example with results are available in Silvaco, both Silvaco website, and it can be accessed through Deckbuild as well. So I'll let you know what is Deckbuild in the later slides, and I'll also show you how to view these already been worked examples, or the basic codes or example codes that are available with respect to different application perspective. I'll definitely show during this training session for the day. Next, the number of simulation standard articles which has been achieved extending back to 1992 are available in Silvaco website. And apart from all these, number of webinars, recorded webinars are available, which are definitely can be accessible by the Silvaco users, and then followed with white papers, presentation materials, so on, and extensive manuals. So Silvaco provide a complete detailed manual for each and every framework, and for each and every interactive tool what they are composed of. And these manuals are like every year they are being like under development, and new models keep on being updated in every manual. So that's a beneficial from the user point of view. And then Silvaco also supports, along with CTT, they support for an active training, seminars, etc. So now let us quickly, without any delay, we'll move on with understanding or obtaining about the Silvaco TCAD products. So we are going to focus mainly towards the process and the device simulator. That is, I'm going to get you people introduced with or get you people exposed to various modules that is available in Silvaco TCAD. First, let us discuss about the process simulation. So process simulation, it's a 2D process simulators are used to simulate, develop, analyze and optimize the semiconductor process fabrication. So it could be of like diffusion and implantation, oxidation, deposition, silicitation, photolithography, etc. So the tool which we use in Silvaco TCAD to perform the process simulation or to undergo to various fabrication steps to create a structure is Athena. It is a process simulation tool. It is so Athena, a few words about Athena. Athena, it's a process simulation framework and that enables the process and integration engineer in order to develop and optimize semiconductor fabrication processes. So it provides us an easy to use, modular and extensible platforms, as I mentioned, like for various fabrication steps. So it may include of like deposition, etching, etc. So Athena basically replaces a costly wafer experiments with simulations in order to deliver a shorter development cycles and along with the higher yields. So this particular, this is the framework of Athena. It's a framework architecture of Athena. So it's basically consisting of two standalone process simulation modules, that is Supreme 4 and Optical module. And it has three add-on modules, that is MC implant, it is nothing but the Monte Carlo implantation simulator. And then we have Elite, and then we have Monte Carlo deposit and etch. So a few words about each and every module we will discuss about it. We'll understand why these modules are required and for what purpose they have been required. So basically process simulation. So Athena is easy to use. It has an easy to use UI interface and it has a powerful plotting tools which can be targeted to TCAD simulation. And if suppose if someone wants to work with the design of experiments or optimization, then in that case they go for a virtual wafer fab, which is a separate tool meant for mainly for developing this, performing this kind of design of experiments of the devices. Moving on further, S Supreme 4, it is it's a 2D core process simulator that is widely used in the semiconductor industry for design, analysis, and optimization of various fabrication technologies. So S Supreme 4 accurately it simulates all the major process steps using a wide range of advanced physical models. So that is for diffusion, implantation, oxidation, epitaxy, etc. Next is we have the MC implant, that is Monte Carlo implantation simulator. So it's physically based an implantation simulator in order to model stopping and ranges in crystalline and amorphous material. It accurately predicts the implant profiles and damage for all major ion or target combinations. And then we have Elite. Elite is like an etch and deposition simulator. It's advanced 2D moving boundary topography simulator for modeling physical etch, deposition, reflow, and we have the CMP planarization processes, etc. And along with Elite, we have the Monte Carlo etch and deposit, which is again going to be an advanced topology simulator. So MC, that is Monte Carlo etch, it's meant for various etching processes which use the flux of atomic particles based on Monte Carlo models. And MC deposit is like for modeling of ion stopping and implant ranges in amorphous and crystalline media, and extensive comparison with measured profiles that have shown that MC implant is highly accurate and it is going to be predictive. So the simulator can be like used for variety of ion or material combinations. So that may include arbitrary geometries, different substrate orientations, implant doses, energies, and angles. So it includes several Monte Carlo based models for simulation of various deposit processes, which again use a flux of atomic particles. And then we have the Optical, which is a 2D optical lithography simulator. It is a non-planar 2D lithography simulator that models all aspects of sub-micron lithographies. So like it just provides a fast and accurate alternate to experimental evaluation of the mask printability and process controls. It simulates both projection imaging and proximity printing with a large mass to resist gap. So from this optolithograph of the submicron lithography, it is categorized as imaging, exposure, photoresist bake, and development. So with this overview of different modules that is present in the process simulator, let me just consolidate the key features of the process simulator, that is Athena. It is fast and accurate simulation of all critical fabrication steps that is used in various devices. I've just projected only a few over here. That is CMOS, bipolar, or any binary material, single element material, or it's going to be trinary, quaternary. Everything is supported by Silvaco TCAD process simulator tool, that is Athena. And then if a user want to perform any optoelectronic device or power-based device technology, so yes, it is also supported by Athena, the process simulator. And it accurately predicts the geometry, dopant distributions, and stressors in the device structure. It is easy to use software integrating the plotting capabilities, automatic mesh generation, and graphical input of process steps. So that accelerates time to production for new process development as well as equipment upgrades. With this key feature about the process simulator Athena, let us quickly move on with the understanding about the device simulation and the various modules available in device simulator. Device simulation is used to simulate the electrical, optical, and thermal behavior of semiconductor devices. Device simulators, they solve the physical models and equations in order to perform the DC, or it could be a AC analysis and time domain simulation. Okay, now comes to the point of like which tool perfectly suits for the device simulation in Silvaco TCAD. So Atlas and Atlas 3D, it's a device simulation software available in Silvaco TCAD in order to perform all these electrical, optical, to understand the thermal behavior of any semiconductor devices. Framework, this particular slide shows the Atlas framework architecture. There are different modules are available in Atlas for performing various simulations using Silvaco TCAD device simulator, that is Atlas. So completely, if a user is working on silicon-based devices, then we have a SPICES module, which is going to be a dedicated module for performing only SPICE, that is for silicon-based devices. That is, if it is a 2D, then it is going to be SPICES. If it is a 3D, then it is device 3D. And a few words, and then Blaze is for compound materials like binary, ternary, quaternary, whatever the material is. If a user is working on a compound semi-based material, then Blaze is a module for component. Apart from that, we have thin film transistor for both 2D and 3D, ferro module for any like ferro devices, and then Vexel module, we have laser, LED, and then apart from all these device simulator, that is apart from these major frameworks, we have if we are performing any quantum confinement effects, we want to see a quantum confinement effects in our device, then we have the quantum 2D and 3D module. If we are analyzing with a noise with respect to the device we are working with, then Silvaco TCAD supports with a 2D noise simulator, noise module. And then for optoelectronic device, we have a dedicated module, which we call it as Luminous 2D. And for 3D structure, we have Luminous 3D. And if a user is working with or want to extract something related to temperature, or would like to analyze the self-heating effects in a device, so in that case, we have the Giga module, both for 3D and for 2D. And apart from that, if it is going to be a simple like a circuit design that you would like to analyze within the Silvaco TCAD itself, that is combining the device and circuit. So in that case, we have mixer mode, both 2D and 3D. And finally, we have the C interpreter, which is a user-defined model. That is, Apart from the models that are by default available in Silvaco, if a user is coming up with a new model and would like to incorporate into the tool and would like to characterize the device by means of using that, yes, it is possible by means of using C interpreter. Definitely during the demonstration, we'll show you the basic templates that are available in Silvaco TCAD as a C interpreter, how to incorporate any user-defined model. With this, let us in detail understand about the each and every module, major modules along. So SPICE's device 3D. So SPICE's, it is a advanced 2D device simulator for silicon-based technology, so that it incorporates both distribution and energy balance transport equations. So a large selection of physical models are available for solar cells, just giving an example. So they may include, for example, if I consider solar cell, they may include bulk mobility model, surface mobility model, recombination model, impact ionization, or if you're working with any tunneling based devices, then tunneling models, variety of tunneling models are being available, and it can be used with respect to this SPICE model. So SPICE module supports for all the different type of physical models. And device 3D is about, it's a 3D device simulator for silicon as well as for other material based technology as well. So they may have support for the DC, AC and time domain characteristic for a variety of material like silicon, or it could be a 3 to 5 material, or 2 to 6, etc. All these material can be analyzed by means of using device 3D. So Blaze is completely like a module that is dedicated for performing any advanced materials. Apart from silicon, if it is going to be any apartment, it could be of binary material. If we are working with the silicon germanium, obviously Blaze module is automatically called or analyzed by the tool, and accordingly this module will be included in during the simulation. Not only for binary material, it could be of trinary like algan, or quaternary, etc. All the compound semiconductors, which it includes libraries of compound semiconductors of binary, ternary, and quaternary material. So Blaze and device 3D, it has a built-in models for a graded and abrupt heterojunction and simulates. Going on with the next module, that is Luminous and Luminous 3D. It's an optoelectronic device module. So Luminous and Luminous 3D are advanced 2D and 3D simulator specifically designed in order to model the light absorption and the photo generation in optoelectronic devices. So exact solution for a general optical sources are obtained using the geometric ray tracing. So this particular feature, it enables this Luminous and Luminous 3D module in order to account for the arbitrary topologies, and then to internal and external reflections and refractions, and polarization dependency and dispersion. It also, this particular module allows the user in order to perform this optical transfer matrix method, use this optical transfer matrix method analysis for coherence effects, suppose if they are working in a layered devices. And then it also includes the beam propagation method to be used to simulate the coherence effects and diffraction. So with this, let me just quickly move on with the next module, that is TFT, thin film transistor. So that is, it supports for 2D and 3D. It's an amorphous and a polycrystalline device simulator. It's an advanced 2D and 3D device technology simulator that is equipped with the physical models and the specialized numerical techniques that is required to simulate the spectral response, like for various, for example, if I take an optoelectronic device, in that case, it helps us to simulate the spectral response of an optoelectronic devices. As we could see, it just simulate various amorphous or polycrystalline devices, including the thin film transistor. So the specialized application, it includes a large area display electronics and solar cells. Then we have Giga module. Giga module is basically, it's a electrothermal, that is non-isothermal device simulator. So it is often combined with the SPICEs or Blaze device simulator, allowing simulation of a local thermal effects. And it includes, with respect to the, like if a user would like to analyze with respect to heat generation, heat flow, lattice heating, heat sink, and would also obtain the effects of local temperature on physical constants. So this particular Giga model has several models that are being available in order to perform all these. And yeah, moving on with the next. We have the mixed mode, 2D and 3D. It is circuit simulation for advanced devices. So a mixed mode 2D, 3D, it works with, again, with the other modules like not only SPICEs, it also works with the Blaze in order to simulate circuits that include physically based devices in addition to compact analytical models. So it simulates the physics-based devices in combination with the analytical models. And any combination of Atlas 2D, 3D module is possible with respect to mixed mode. And devices that is simulated, that is from mixed mode, the devices simulated with the SPICE netlist circuit description. So it provides a wide range of SPICE models. That is mixed mode provides us with the wide range of SPICE models. And yeah, with this, moving on with the quantum 2D and 3D, which is going to be the simulation model for quantum confinement effects. So quantum provides a set of powerful modules for simulation of various effects of quantum confinement of the carriers in the devices. It supports with this Schrodinger Poisson solver, allowing the calculation of the bound state energies, wave functions with respect to the electrostatic potential. And then a quantum moment model allows the simulation of a confinement effects on the carrier transport effects. Let me consolidate the key features of the device simulator, that is Atlas and Atlas 3D. So Atlas and module, the framework, it accurately characterizes the physics-based devices for performing any electrical, optical, and thermal performance without any costly split lot experiments. It solves the yield and process variation problems for various applications, and optimal combination of with respect to the speed, power, density, or if you like to calculate the breakdown of the device or leakage, or with respect or from the reliability perspective. So everything is made possible by means of using the device simulator Atlas, and it is completely integrated with the Athena, that is the process simulator. So also along with the visualization package, extensive database of examples. So what does it mean? Like, so if a structure, we have undergone various fabrication steps using the process simulator Athena, and a structure is ready, which need to be characterized, where we, that is characterized means like including the physics models, providing the biasing condition. All these are taken further to the Atlas, the device simulator. So we undergo various fabrication steps, we create a structure, we take forward to Atlas directly, where we include the physics models, biasing, in order to characterize the device for various analysis, to perform various analysis, which may include a transient, or it may include a AC or DC analysis. With this, we'll get introduced with the interactive tools. So the process, knowing about the process simulator, knowledge about the process simulator and the device simulator is must. Apart from those, knowledge about the interactive tools that is available in Silvaco TCAD is also found to be key significance, because these interactive tools is what is going to help us to write the scripting, simulate it, and visualize the device that we create, visualize the plot that we have obtained. All these results, everything is made possible, viewed directly by means of using the various interactive tools. So they are a suite of applications that provide the GUI-based pre and post processing services to Silvaco TCAD simulators. So they offer with the easy to use GUI interface, and they have a powerful plotting tool that is targeted to TCAD simulations. And then they are provided with an interactive runtime environment with automatic optimizer. So with this brief overview of the interactive tools, let us quickly have a view of what are all the tools that is available in this category. We have Deckbuild, which is an interactive runtime environment. So Deckbuild is a platform where we write all our scripting with respect to the process simulation or with respect to the device simulation. So it is going to be a window, a platform where all these inputs are being provided. Next, Mask View, it's an integrated layout editor. Then we have DevEdit, which is a structure and mesh editor. So for example, like a user have created undergone a various fabrication steps and have created a structure in the process simulator. But there is a default meshing in Silvaco TCAD Athena process simulator, which cannot be changed later, because if we change, it will affect the accuracy level of our device performance. So in order to overcome that particular problem, we may take the structure to the DevEdit, which is a structure editor, where you can go for mirroring the structure or cropping the structure or removing region from a structure, or you play with the editing the mesh part in a structure and then take further to the device simulator for characterization. So this particular tool, DevEdit, is mainly meant for either creating a structure from scratch or editing a structure that's been created using the Athena tool, and then we can edit the mesh that has been already defined in the structure. So everything is made possible by means of using the DevEdit tool. And then TonyPlot and TonyPlot 3D is a visualization tool. That is, we have created the structure, we have simulated it, but we want to view the structure. So in that case, to view the structure, we have this specific tool called TonyPlot, and TonyPlot 3D is to view the three-dimensional structure. And then for viewing the plot also we'll be using the same TonyPlot. And there are several features that are available in TonyPlot. So once after this presentation, definitely I'll give you a quick overview how this TonyPlot looks like and what all the other feature that is available. Because I have told you previously, it's like in TCAD software, you can understand what is happening inside the device. So this visualization is made possible by means of using the tool TonyPlot. It is if you want to see, for example, like the electric field that in your device you want to see with respect to the plot or with respect to the device, then it can be viewed. Or you want to see the electron concentration, or your it could be of anything, a potential distribution, or you want to see the band gap during your off and on state of your device, and you want to compare it with respect to the mechanism that you're working with. So everything is made possible by means of using this tool TonyPlot. Okay, moving on further. A few more detail about these tools. So this is how a Deckbuild look like. I've attached a picture for your reference, but do not worry, like while we go for demonstration, we'll have it in a better view and better perspective to understand about it. So it's like it's fully documented and it supports with a searchable example database. So Deckbuild, and then it provides us with a runtime output. So generally this Deckbuild will be split into two. One to write our scripting, another while during simulation to view our results. Definitely later session we'll see how it is going to be. And then it supports with a variable outputs. It provides a separate column to see our outputs, and then a variable panel to track our variables and the files that we have simulated during our simulations. Okay. So with this, let me just quickly project you with some like examples with respect to different applications that is available in Silvaco. So there are a number of applications, a number of devices that can be simulated using Silvaco TCAD, but due to the time constraint, we will just focus on few applications and few concepts that is behind Silvaco TCAD and what are the parameters, different parameters that can be extracted. So from the optoelectronic simulation perspective, optoelectronic simulation, so we have the model light absorption and photo generation in devices. And I've already mentioned like it supports with the arbitrary topologies. It allows for understanding about the internal and external reflections and refractions, polarization dependency and dispersion. And then optical source can be monochromatic or multispectral as well. It is supported by Silvaco tool. And then we can perform for the same device, we can perform a DC, AC, and transient response. Further, with respect to the physics option available for the right simulation, it includes the ray tracing method, transfer matrix method, beam propagation method, and finite difference time domain method. So right now, all these methods are being like available to the user in order to perform their optical simulation in using Silvaco TCAD. Yes, we are still under development, like much more new features, new models, new physics-based methods are to be introduced soon. Then defining the light source shape. So so these are some example, like we can define it with a source with respect to elliptical model, or it can be a user-defined optical source, or it could be like a Gaussian source. In this case, it's a Gaussian source intensity with a normal incidence and a periodic boundaries. And like you can use an ASCII file, and then we can go for a user-defined optical source, which can be included within the tool. Next, with respect to light absorption, like I have taken few examples with respect to absorption, that is solar cells. So Silvaco TCAD, obviously it supports with the solar cells, and many material and design types are being used in solar cells. So it could be like if you want to perform any textured solar cells, or you work with any lens-based dye-synthesized solar cells. There are so many features. So you could see like texture, if the material is going to be like surface is going to be textured, or if you have lens-based surface roughness is included. Anything can be made possible by means of using Silvaco TCAD. And with respect to light emission, I've just chosen LED as an example, where you can simulate LED with respect, including the quantum effects, or if you want to analyze the self-heating analysis of the devices, yes, it could be performed by means of using Silvaco TCAD. Another example of light emission, VXL. Yeah, so these are some examples we have been projected over here with respect to VXL. Waveguides. So waveguides, we have a separate module, laser module, in order to perform the simulations of waveguides using Silvaco TCAD, and it's suitable for the beam propagation method. Next is about the power devices simulation. Like a few examples that's been placed before you people. Before that, we would like to talk about the physics that is available for like either it could be a GaN specific process simulations, because when we consider the power devices like a wide band gap semiconductor, they hold a great promise in order to significantly outperform and eventually replace the traditional silicon-based electronics, that is power electronics technology. So there are like several research and development efforts like in other wide bandgap semiconductors are going on, but still GaN and of course a silicon carbide based material, they have reached a level of maturity that allow their use in the power electronic application. So they have enabled the development of a high power density, cost effective, energy efficient and robust power component. So while the wide bandgap technology offer a significant capability that can improve the power electronic industry, meanwhile, the industry also should overcome numerous challenges, that is including high material and manufacturing cost, also from reliably manufacturing these devices at high volumes, also along with the competitive cost across the full range of power electronic applications. So effective process and device simulation for wide bandgap semiconductors will found to be an important feature to bridge these gaps. So from that perspective, Silvaco TCAD provides a specific physics for like a major material of like GaN, silicon carbide. Yes, it is support for other material as well. So here in this case, in this particular slide, we could see the GaN specific process simulation physics. So it supports for an automated piezoelectric charge and then external strain generated piezoelectric charge. It just provides us with a calibrated implant activation and diffusion models. GaN specific device physics simulation, they include this anisotropic high field mobility and then automated calculation of a spontaneous and piezoelectric charge and then impact ionization. Yes, optical absorption also made possible. A few results, measured results with respect to simulation verified by numerous measured results have been projected over here. And then a few examples. So that is FET application with respect to self-heating, that is self-heating effects. So like for GaN FETs, when they have been like grown on a sapphire or a silicon carbide substrate, the self-heating effects are significant. So like this particular picture just provides us with when they have been created using a silicon carbide as sapphire, what happens to their results. So this provides with the transconductance and the drain current values. Comparison, that is, we can even overlay the plots and we can have an easy comparison of various parameters. So in this case, two different substrates have been chosen and their current along with the transconductance. So how the transconductance provide the effect on the current has been shown over here. Then moving on further, this is a plot which just shows an individual plot of sapphire and silicon carbide with respect to the IDVD characteristic, that is output characteristics. So yeah. And yeah, next is about enhancement mode in polar GaN MOSFETs. So these are few kind of applications that we see that could be performed using Silvaco TCAD. There is a growing interest in high performance enhancement mode GaN channel devices, majorly because of their single voltage operation and simpler circuit topology. So the advantages of the enhancement mode GaN FETs, when they are fabricated on an N-polar GaN, they include a reduced source drain axis resistance and a wide band gap barrier layers that is being used for polarization induced, like for example, if I take this GaN FET devices, so allowing this 2 dg depletion under the channel. And next is about GaN thermal optimization using flip chip structure. Although the superiority of GaN FET device characteristic had been demonstrated, the self-heating effect is always found to be a hindrance for the production of a high power and a high speed GaN based switching devices. So this effect can be significantly reduced by the cost effective heat sink approach. And in this particular example, like what I have projected over here, this provides us to understand and control the self-heating effect of the GaN FET with a flip chip concept, and that's been simulated and the device characteristic are compared along with the normal structure that's been projected. Okay, so this is a normal structure and this consists of a flip chip structure, and the results of the same are also being compared over here. Next, moving on with the silicon carbide devices. So as I have already mentioned, like GaN, silicon carbide is all like now being like completely or continuously being researched by many researchers around the globe. They work on this wide band gap material. They have attracted so much, mainly it is going to like, it provides with the temperature dependent velocity of silicon field characteristic, and it supports Silvaco TCAD supports for the anisotropic mobility and impact ionization rates. Okay, then yeah, this is an example with respect to Monte Carlo phosphorus implantation into the silicon carbide that's been projected over here. So deep implantation is being possible in silicon carbide, okay, and that's been projected over here. And this is a nitrogen Monte Carlo implant into the silicon carbide trench. And this is an example for like performing stress simulation. So this shows the reactive ion etching, that is stress effect formed during the mask patterning after the reactive ion etching. And here we could see high compressive stress in the X direction has been distributed. So Athena can perform the stress simulation analysis as well. So what we can do is, after performing the stress analysis in the Athena, we can take forward to the device simulator Atlas. So this stress calculation which we have performed in Athena will also be taken into consideration while characterizing the device. And this is an example with respect to IGBT, that is insulated gate bipolar transistor, and the collector current versus the collector voltage is being projected over here. Yeah, this is a particular slide showing about this is what I told you. We can easily understand what is happening inside the device. So this particular plot shows the electric field analysis. So we can this is possible for all the devices. So we can understand what is happening inside the device, why the device is behaving in a different manner. So what are the parameters that need to be tuned or optimized in order to obtain the results of what we expect. So this is a particular example showing with respect to breakdown analysis, breakdown voltage. So IGBT structure that is showing different distribution. So we could see the electric field distribution of the device, potential distribution, or impact ionization rate distribution, but these are not limited. There are a number of like distributions that you can see either as a plot or the analysis in the device itself. So both are being possible. And this is an example for simulation of a 5000 volt breakdown voltage of the IGBT device. And yeah, so for various temperatures. So this is calculated for 203 Kelvin, and this is calculated for 300 Kelvin, the breakdown voltage, and the leakage current, which is in turn, it's going to depend upon the lattice temperature. So for various temperature, the breakdown analysis has been performed. And we could see the overlay plot and the easy comparison of that is various temperature breakdown voltage simulation has been performed, and we can compare it easily using Silvaco Tony plot tool. Okay, so that's all about this presentation, and I'm just projecting you people with various products summary that is available in Silvaco. It's not, we are not limited only with respect to TCAD. There are a number of devices, including that is with respect to the spice simulation or model extraction or custom design. It could be, or it could be variation analysis. So from all the perspective, Silvaco or like provides the solution by just providing the tools to their extended customers. Then a summary for this particular presentation is as follows. So the Silvaco is a global EDA leader, driving growth in order to provide the value to our customers in advanced IC, display, and power. So TCAD, that is physics device simulation, it captures theoretical knowledge in order to provide the essential insight. So they can predict behavior in the entire design space. So TCAD simulations, it provides like the data even which is going to be very difficult to measure, and also it's going to help us to speed up the innovation and the development cycles. And it supports with complemented with interactive tools and automation. And as I shown before, like it supports with an extensible additional sources are available in Silvaco. So yeah, thank you. So with this, if you have any doubt, I think we can just clarify it right now with respect to this presentation. If not, I can just show the interactive tools. I can give you the overview of interactive tools. Okay, shall we move on with like projecting with respect to the interactive tools that is available in Silvaco TCAD?
Yes, yes.
Okay, thank you. So, So this is what Deckbuild is about. So I told Deckbuild is a very important interactive tool where we give the input, we simulate, and we obtain the output result. So this is how the platform is going to be. So it consists of majorly of two windows. It is divided into two. The first, the topmost, is where we input the code scripting and we simulate it, and the bottom part where we view the output. Okay, that is runtime output, and whatever we have simulated, the variables will be displayed over here. And yeah, here in this case, the resource usage, like how much memory we have used, all these will be displayed over here. I'm not going to write this scripting right now because after a break in this morning session, we are going to start with the process simulator. So during which we'll be having a better view than I just show like orally. So you'll have a practical demonstration of the same. So let me just quickly introduce you with all these like icons over here. So you have the play, you have pause, you have stop, you can kill the simulations, you can kill and start, refresh, restart the simulations. And then for example, you have several lines, and out of those several lines, if suppose if your simulation is going to take much time, your structure is very complex, so in that case it is taking much time, so you want to simulate it back. You have already simulated once, a particular data is being saved in the library or in the folder where you are simulating the input code, and right now you want to start your simulation from a particular line. So in that case you have an option called go to line, and then like this is Tony plot viewing, opening a Tony plot, and this particular icon is opening your 3D Tony plot, and this is for opening your mask view layout designer, and then this is for opening the dev edit. So everything, all other interactive tool can be easily accessed from the Deckbuild platform itself. Okay, and then you have several options like so major options alone, let me explain. So you have you have the option of tools that you could see, whatever you have seen outside, that is Tony plot 3D, mask view, everything is you can obtain from this tool perspective. Then this commands is like majorly important because few people like maybe very like they will be a beginner using TCAD tools. So I've already mentioned that Silvaco TCAD supports with the GUI based. So in this case, apart from GUI based, you have this command scripting as well. That is, rather than until you get practice, we request people to go for using this kind of like what to say commands where you just use the GUI based. So let me just open one for your reference. So you can select the impurity among the one which has been provided. You can select the dose. You can select the model, whether it is going to be a Monte Carlo or dual Pearson or Gaussian. So then which degree you want your angle, I mean like your device to be tilted, rotated, whether it is a crystalline or amorphous one. So for example, if you're taking a wafer, so in which case you will be defining it, and then point defects, dislocation loop. So everything you can provide it over here and just give a write in this option. Once you've done that, automatically the particular line will be written over here. So this is for beginners. So in the initial stage, until you get practice with the tool, we recommend you like to go ahead with this. And then similarly, like if you're working with a structure and you want to mirror a structure, in that case, you would like to like rather than like you don't know which syntax to be used. So in that case also, you can have an option of selecting it GUI based, whether you want to mirror your device to the right or to the left. And then apart from all these, you have written the scripting and you want to extract few parameters like a material thickness, or you want to extract something with respect to junction depth or surface concentration, just something that with respect to your device. So you can update it by means of selecting, these are available in default, but it's not limited to as well. You can write your own, with respect to your analytical calculation, you can write the expression and get your value extracted from the device, what you have performed. And similarly, it is available for the device simulator too, like if you want to obtain the leakage current, or you want to obtain the on current of your device, that is ID current, and then you want to see the subthreshold current, or you want to see the subthreshold threshold value, or you want to obtain like user defined means it is going to, like, you can write your own expression. Like in this case, these are the default that is available. If suppose if you want to extract the transconductance from the IDVG curve, so in that case you can write the expression and just click the option, right? So it will be automatically written into this platform. So apart from all these, this particular it shows the models that is available in Silvaco process simulator, that is Athena. So different models that are being available. So it just projects the different available model. And if suppose, as I mentioned earlier, if a user comes up with a new model and they want to include it within the tool, TCAD tool, so in that case, we have the C interpreter templates for different models. So if you want to work with an, if you want to implement or include an electron velocity saturation model, then you have the template for the same. It's a C interpreter templates. And then if you want to analyze for various category, it's available for various category. That is, if you're going for position dependent, and then you're going for like you could see recombination, everything with respect to temperature analysis. For everything, you have the template over here. This is not limited only to the process simulator. This similarly you have for Atlas default models. So you can easily check what are the default models, and for default material detail available in Atlas. And then you can also go for the C interpreter template models. So that's available for various models. So like I have this SRH lifetime if you want to edit it. So how do I go for it? So you can edit in this template and include within your device simulator too. So this structures models is for device simulator. So like you see mobility model, there are so many, and then recombination model, statistics model, impact ionization model, tunneling model. So you can select and write and give the right options. So this is for at the initial stage. So once if you are like fine with the tool, you're ready to carry out with your own scripting, and you're comfortable using the syntax and the TCAD tool, then you can automatically start writing your scripting. And we will also let you know what are the basic, where you are supposed to start. For example, if you're performing a device simulation, so what is the first step that you need to define in writing the scripting, and followed with what are the other particular models, and then how do you go for the solve statement, how do you define the biasing, step by step we can view it in the later sessions. Okay, so this is what about Deckbuild. Let me just quickly open Tonyplot. So Tonyplot, as I mentioned, this is the visualization tool. So yeah, I'm just quickly opening a structure for your reference. Yeah, so this is a basic VGT structure. So you could see, you can view the device, okay, and you can see it has an option called display option, where you can see, for example, if you are gone with some doping for the device, so you have the contours, you can select and just give apply, and you can see what all the doping effects is being seen here. So let me select it as total doping. So this is what the doping analysis, and you can see the ranges of it. And then if you are going for, if you want to see the electrodes that you have applied to this particular device, you can have the option. So you could see the emitter, base, collector. So you can view the electrode option, and junction if you want to see. Yes, you can see the junction lines. And this is already simulated once. I'm just showing it for your reference. like how all these works in Tonyplot. So Tonyplot is not only to view your structure or view your plot, but apart from that, it helps you to see what is actually happening within the device. And if you want to see your mesh that you have defined, you can see the meshing for the devices that you're working with, that which is being defined by you, defined by the user. And then there are so many features. We can take a cut line. So let me just quickly show you one particular example. So you could see here, this is by default showing the total doping because I have my profile to be of total doping for this particular device. Now, if I can just, I just go right click, give display. And if I want to see the electron concentration and then the potential, or it is going to be a donor concentration, or like this is with respect to structure created using Athena. So active arsenic I can see, active boron I can see. If I have characterized it using device simulator, then the electron concentration, hole concentration, potential distribution, electric field, all these will be displayed over here. So this in detail we'll see in the later session. So this is just to tell you like, okay, Tonyplot helps you to see what is happening inside your device. So just for that particular knowledge. And this is Tonyplot 3D. So it opens a 3D structure. So let me see any 3D structure available. I don't remember, like I have simulated it. Yeah, this is a 3D structure. Okay. So we could see this is a 3D structure. So yeah, so we can view from the perspective, and it is just showing along with the electrodes. So yeah, again, you can take this from the 3D, you can take the 2D perspective as well. So you can have this axis settings, and you can choose whether it should be from the XY plane or XZ plane or YZ plane, accordingly which position you want it. And then you want to reverse your axis, swap your axis, then you can save this particular like 2D images and go for further analysis. So from a 3D, you can slice and take your 2D image as well. So this is what about Tonyplot 3D. There are a number of features are available. While discussing, we will just show you. So this is contours. As I mentioned, like if we are provided with doping, then if we click the contours, then the doping profile will be shown over here. Yes, and then this is with respect to meshing. So you can see the meshing of the device. Yes, so let me zoom. So we can see how far the meshing is about and how the meshing is being defined in this particular like cross section. So for various things, we can adjust, we can manage this meshing. Like for example, it's always recommended to go for a coarse meshing throughout the device and go for a fine meshing in the region which is actually required. So in this case, you could see like there's a coarse meshing entire device, and the region which we prefer, we are provided with a fine meshing. So this is what about meshing detail. Like we'll see how to define this fine mesh, how to define this coarse mesh, how it is going to affect the performance of the device. So everything we'll see while demonstrating or while providing you with an example scripting. Okay, so this is what about Tonyplot. Similarly, you have the DevEdit tool. Yeah, this is a DevEdit 2D. DevEdit 3D is also available. So DevEdit 2D is like you can create a structure from the scratch. So this is completely GUI based. Okay, so you can include a region or remove a region, and then you can mirror a device or mirror a particular region of your device, or you can edit the mesh. Everything is made possible using DevEdit. Okay, so this is simply, I can say it's a completely GUI based structure and mesh editor. So if I have created a structure using Athena, I can take forward to the Deckbuild. I can mesh remesh it, and then further fed it to the device simulator atlas for further characterization. So this is what about the interactive, like overview of the interactive tools. So yeah, definitely during demonstration, we can see in depth about or have better knowledge about like each and every icon that is present in this interactive tools. Okay. So with this, I will stop right now. So I think if you have any doubt, you can just get it clarified. If not, we can go for a break and we can resume back after the break. And we'll start with the demonstration of the process simulator, that is Athena. So let me stop sharing my screen.
Playing is called the Deckbuild. So inside this Deckbuild only, we are going to write our creations. Like you want to make your own structure. That structure you are going to create. We are going to develop and design. So this work area is where the user need to give an input data and as a code. Okay, so where how the structure and so how your device simulation should be occur, and everything around 95% of the user input data is given inside this work area. And so you can see in the bottom part, you can see what is the background simulations. Okay, so let's say here I made some electrical characteristic simulations, like gate voltage. I'm changing it in from different voltages, and you can see different um, background simulations is been carried out to obtain our device's result. Okay, so in this area you can see all this uh, background simulation data will be displayed over here. And you can see here, so in the right hand side, you can see variable history and outputs. So variable history is basically like if you are giving any type of variable, like if you are adding any variable or you are doing some formula calculations. So those things will be displayed over the variable history area. And the output is output window, what it shows is, um, so in your input decode, like you are creating a structure or you are solving some you're solving your device with the physical models. So how what are the files will be generated due to your input data. So those files, everything will be shown here. Okay, so here I'm going to show you one basic example of MOSFET, how it will be created in a Athena using a fabrication steps. Okay, so before that, I'm going to explain you. So the basic thing um, in this deck build input code. Okay, you can see here there are line by line there is a different commands and different syntax has been written. So if you are running this, okay, so you can see the green play button is there, which is save and run the simulation, and you just run the simulations. Okay, so if you run it, the simulation will be carried out line by line. Okay, so for example, initially it will go with Go Athena, so which will basically call all the framework of the process simulator, and it will go for meshing, and line by line it will simulate. Okay, and so this you need to know. And the second thing is this ash. So ash is basically called comment. Okay, so so if you write ash symbol before any type of line, so it is a comment, it will take as a comment and it will be ignored at the time of simulation. And the followed by that, there is some syntaxes or like saving your structure and plotting the log, saving the log file. So that we'll see line by line. you want to characterize the basic output characteristics of your device. So the simulation time will take for this device will take around 10 minutes. And you want to increase the accuracy, and you have increased the meshing, which is increasing the triangles. So it may take around half an hour or 1 hour. Okay. So according to your meshing. Okay. So the meshing is an important part. While working with the TCAD. So for that, I'm choosing initially line, okay, and x defines x axis, and the location will be 0. And so you can see here, it starts with 0 and ends with 2, okay, 2 microns. So in between, you can see some gate, source and drain contacts, okay. So for that, I choose a different locations, like you can see location, which is 0 to 0.2 will be source, and 0.2 to 0.4 will be your channel, and gate oxide will be present, and gate electrode will also be present. And followed by that, from channel to your drain, okay, uh, those, those locations, like basically you are giving the work area of your uh, device, it should be created, okay. And followed by that, you are including the spacing, okay. So SPAC defines as spacing, okay. So spacing is what it is it's a multiplication factor of the triangles which created in the structure, okay. So here you can see 0 to 2, I'm giving the spacing around 0.1, so which is around 100 nanometers. So only 100 nanometer the meshing will be generated, okay. And so here this is a channel area here. So in this channel area, the most of the electrons and holes will be transported. All those calculations, the main area, I'm reducing the spacing to increase the triangles, okay. That's why I gave 6 nanometer as a spacing, okay. So if you want in particular area, you want more triangles, which is more mesh, you can increase by using the spacing. As well as goes for the y-axis, you need to provide it, okay. So the y-axis will be 0 and ends with 0.8 microns. And so followed by that, initially you have given you have called your framework, and you have given the meshing. And so now you need to include a material inside, okay. Let's say you are having a fabricator. So initially you have to include some material. What are the material you want, okay. Like let's say silicon you want, okay. And you want to adding the silicon material, like installing the silicon material into the fabricator. So that is what it is, okay. So INIT defines initialize, okay, and the orientation of the material, okay. Since it's a silicon, so we are using 100 orientation, which is basically a crystal lattice of the silicon, okay. And followed by that, I'm giving phosphorus doping, okay, at 1 e power 14, and the spacing I'm generating here as 5, okay. So I'm going to just simulate only one line, okay. So to show you that, I'm going to save the structure from here. So the command will be save out, okay, out file equal to, and so you can give any name to save the structure. Let's say you can give demo dot. So it should be saved in the extension of dot str, okay. And you can see in the below statement also some command is there. Once you run, so it will run completely, okay. So it will go below this line. So if you don't want to go below this line, you can stop this by typing quit command, okay. So let me just run it from so let me run it. So you can see it, it's taking from the first line. And it will simulate until the quit command. Okay, so it once it reaches to quit, it will stops. Okay, so now let me expand the output file and show you how it has been taken. It okay, so initially it taken Go Athena. Okay, so once Go Athena is called, you can see some the framework. So it will enable all the what are the required process simulator based frameworks. You can see Athena framework is enabled. Supreme 4 is enabled, Monte Carlo is enabled, Allied etch and deposit and lithography. Okay, so these are the modules which is required for Athena process simulator. So those things will be enabled in the initial case, and followed by that, okay, so it chooses a meshing. Okay, so it will take the meshing parameters, and so it will take the basic material it need to be incorporate with it, and finally it will save it in this demo.str. Okay, so let me just plot this demo.str and show you. So to plot this, you can directly open Tony plot and you can open the demo.str, and or else you can just right click and you can plot the demo.str. Okay, so you can see this is the structure it is. Okay, and you can just see how the silicon material has been installed. Okay, so you can see here. Okay, the x-axis will be 0 to 8, 0.8 as we given, and the y-axis you are seeing in a log file. So because we haven't declared how the silicon region need to be formed, so we just initialized the silicon. So now the structure is in one-dimensional. It's not a two-dimensional structure. Okay, and you can see since we use the phosphorus doping, you can see the phosphorus in a graph. Okay, so how the material, the silicon and phosphorus has been added. Okay, and let me go to the second line. The second line is called, so let me copy paste cut paste to this area. Okay, so now so what will happen is so it will initialize the silicon material and it will do some diffusion. Okay, so what is diffusion is in a fabrication procedure. So diffusion means you're heating your material. Like let's say the silicon is there, silicon is added, and basically you are heating it. Okay, and the time of 30 minutes. Okay, so every time, if you give time equal to, so it will be in minutes. Okay, like if you want to go to 1 hour, you can give 60 minutes. Okay, likewise you can do, and time equal to 30 minutes, and the temperature equal to 1000 degree. Okay, 1000 degree in Celsius. Okay, so what will happen is your silicon will be heated at 1000 degree. Okay, and at the time of 30 minutes, and so in between this operation will be happening. So you are introducing one gas inside, it's called oxygen. Okay, so which is called dry O2. So what is this dry O2 and wet O2 is there? So dry O2 means the oxygen will be introduced in a dry form. Okay, and the wet form means it will be in liquid form. Okay, so what will happen is silicon is heated up. Okay, at the temperature of 1000 degree at 30 minutes. So in this 30 minutes, you are including the oxygen. So what will happen is the silicon will react with oxygen and forms the silicon oxide. Okay, so this process is called oxidation process. Okay, so which will be done in it will be done in various materials, like let's say you are using iron. And if you oxidize the iron with oxygen, you can get iron oxide. Like aluminum you take, and if you oxidize the aluminum metal, you will get aluminum oxide. Okay, so followed by that, they give some command called press. Press means pressure. So it's an atomic pressure which should be present in this chamber. And the HCl is an error factor of your fabricator. Let's say you are doing your own fabricator in fabrication in your lab, and so the machine will be having the error factor. Like, so the machine will be having different error factors, like in the manufacturing itself they will include this. So those error factor you can define, so you can give it as a 3 or 1. So based on the manufacturer it's required. Okay, and if you don't want to give it also, it will take it as a default as 1. Okay, so here I'm just representing you to how to use the error factor. Just I'm giving it as a 3. Okay, so now let me just simulate this. Okay, so it will stop at the quit. And so let me open the structure directly. Okay, like you can right click the structure demo and you can give plot. Okay, so I think it will take some time to load. Okay, so you can see here. Okay, so we have so there is a silicon we have included at the beginning, and due to this oxidation process, we made a silicon oxide. Okay, so silicon plus oxygen with a temperature at 1000 degree at the time of 30 minutes. So which forms a silicon oxide. Okay, so if you have any doubts, you can ask. Okay.
Hello.
Yes.
Yes, sir. Yeah, actually, if we go for some another material, like if we are going for the polymers and we
Okay.
are using some different gases in place of oxygen, so
Okay.
what happen in that case?
So let me show you. Like actually, you cannot include different gases. So
Okay,
let me show you.
for example, we need to heat up the sample
Hmm.
in some different gas environment for different time. So what
Okay.
will we have to do?
Yes. So let's say I'll show you one command. Okay. So these are the things like dry O2 and wet O2 and nitrogen and gas flow. Like you can use a different like H2O, HCl. Okay, O2, N2, H2. Okay, so based on that you can change. Okay,
Okay.
so let's say you want so now I'm giving dry O2, and HCl you can give 3% as given. The pressure will be 1 atoms, and the temperature you can set accordingly, and the impurities you can add, like different material impurities. Okay,
Okay.
so the boron, phosphorus, silicon, okay, zinc, selenium. So only these materials you can use in this process. So different polymer you said, so these things cannot be done.
Okay, my actually my question is that you are taking is for the diffusion process exactly.
Yes, yes.
Okay, my question is that if I have deposited some film
Okay,
on some base substrate, and we need to go for the heating process in
okay,
some different gas environment.
Okay.
What happened in that case?
Okay. So let me show you, tell you in the silicon itself. Is that fine?
No, I'm talking about the some different material. If in place of silicon, like if we are using polymers, like for example, PCBM.
Okay. So the PCBM material, I think it's not available. So let me check in the manual. Okay, so the PCBM material is not available, okay, in Silvaco. For that, what you can do is, so you can do user-defined materials, okay, like, so that we cannot do in process. We can do, we can call this user-defined function in device simulator, okay.
Okay.
Like you can include the user-defined material and
Okay.
PCBM, and
Okay.
some parameters are available like band gap, permittivity, uh, okay, and the conduction band, balance band, Fermi level. So all those parameters you can give, and along with that you can include the Sopra database also, okay.
Okay.
And if you have the Sopra database, that also you can include, or if you don't have the Sopra database, you can give the equivalent material.
Okay.
Okay, so equivalent, like, so the command, it's like the default, uh, uh, so let's say the silicon and the polysilicon, which is will be having the same crystalline structure, okay.
Okay.
And
Okay.
we can use polysilicon as a default material, okay. So likewise you can choose those, and you can choose different values,
Okay.
band gap, permittivity, and so there are around 50 extra parameters are there. You can include
Okay.
all those things, and you can include those materials here.
Okay. Means for adding some new material, we have to go into the device process first of all.
Yes,
Then we
device
can
simulation.
fetch that particular material from there to in this console.
Yes, you can do that.
Okay. So anyway, you can go for the further.
Okay. So I think I have one example. Okay, sir. In the evening session, I'll show you the
Yeah,
example
yeah,
of
sure,
how
sure.
to do the user-defined material. Okay.
Sure, sir. You can continue on.
Yeah, sure. So here, up to here, so we have made silicon, and we do some oxidation process, and we will remove this, okay, oxide, so which is present, which is called etch oxide. Okay, so what will happen is it will etch the topmost layer of it. around 0.02 microns, whatever the oxide will be there, it will be etched out. So let me plot this before that and let me run this. Okay, so you can see here, so in the left hand side, which is a previous structure, and right hand side, it's a new structure. Okay, you can see the oxide in the SiO2, so it will be removed. Okay, so it's kind of thick, and here it's less because so we have removed some top layer of the oxide. Okay, using the etch statement. So etch and oxide at the thickness of 0.02. Okay, and if you want to increase, then you can do that also. Okay, and followed by that, so we are going to form a P-well implantation. Okay, uh, so this device, I'm going to use it for an NMOS. Okay, so for that, I'm going to implant a P-well at the initial case. Okay, so for that, the syntax is implant, and the impurity will be boron, and the dose, the concentration dose will be 80 power 12, and energy is set to be 100 EV. Okay, the 100 EV. The Pierce is a model name. Okay, so in the fabricator, like if you're doing in a physical fabricator, the Pierce statement will not be an issue. And if you include this Pierce, so the set of implantation iteration will be calculated for this implantation profile, and accordingly the implantation will be occurred. So in meanwhile, you are including the diffusion, and so you are heating your material at the time of implantation. Okay, the temperature will be 950 and the time of 100 minutes. So here I'm using wet O2, and so HCl is an error factor. So let me go to the next thing, so which is implanting an N-well. Okay, so here you introduce some heat. Okay, so if there is a if you want to your device should be the physically strong, so there is the temperature changes you can include, like, so initially like 950 you have given us a temperature, so later you increase the temperature, and step by step you increase it to 1200, and you introduce this nitrogen and press pressure at one atom, and followed by that you increase again 1200 at different timing. So it's like silicon, the SiO2 region will increase, okay, at the different temperature constraints and different timing. So let me run this. Okay, and so before structure, this is what the before structure is, and so here you can see here the phosphorus doping has been added like 1e14, and so in the oxide region you can see that there is no doping. Okay, it's completely comes to the zero. Okay, So in the coming structure, let me show you. Okay, so in this right hand side structure, you can see due to different doping, different diffusion, the SiO2 size has been increased, and you can see here. Okay, so different like you have introduced the boron concentration, boron impurities and phosphorus impurities. Okay, the phosphorus, it will be set to 1 e power 14, and the boron will be like so 1 e power 16. Okay, so it will be around, if you just zoom here and you can see here, okay, there is some curve. Okay, so due to this SiO2, the boron, this phosphorus doping has been made in such a way. Okay, so so why I made this SiO2 is it's kind of sacrificial layer to form a substantial doping profile. Okay, so now the second step, what I'm going to do is removing all the oxide, which is SiO2. I will just remove it. So for the statement will be etch oxide all. Okay, so previously you can see the doping profile is like constant. Okay, so now it's kind of substantial type of doping. So for that we need SiO2 in the top. For that I use the SiO2. So now we just remove it, and so to make this SiO2 in oxide layer, we should not do any doping, but still here there is some doping profile is been added. So we'll just remove it and make a new SiO2 region. So for the syntax will be etch, oxide and all. Okay, so this is your structure in previous. Let me open the new structure. Okay, so whatever the oxide which is present will be which has been removed. So because in oxide we added some doping profile that we have removed. So now we can add a new SiO2, so which will be around 0 doping. Okay, and followed by that. Okay, so in meanwhile, okay, when while creating a structure, you are doing etching, deposition and annealing. So different thing will be happen. Okay, so due to this, maybe the top layer of the silicon will be get like some impurities will be added. So maybe it's not clean. Okay, to clean this, we use the process called depositing the oxide, and we remove it. Okay, the top layer, the completely it will remove. Okay, so it's kind of sacrificial cleaning oxide way. So which is diffusion at the, so diffusing the temperature and oxygen you are including at the time of 20 minutes, and finally it's just removing the oxide. Okay, so let me just run this and show you. Okay, so let me run this. So let me plot this. So what will happen is, so due to, so we are including again SiO2 as a sacrificial cleaning oxide layer. And so again, we'll remove all the oxide. Okay. So what will happen is, what are the top, so if any top layer of your material, silicon will get some unwanted impurities will be removed. So the top layer will be clean. Okay. So for that purpose, we are doing this. So let me just run this again. And followed by that, so now we'll do this gate oxide. Okay. So let me just plot this. So here the gate oxide has been created and it's removed here. Okay. And followed by that, so now, so we are actually we are going to use the gate oxide here for our gate, the gate oxide. So that here the diffusion, the time will be 11 minutes and the temperature is 925. Okay, 925 and dry O2, and as usual as the pressure and the error factor. So let me just put this in the code in the top. So you all know, so if you include this diffusion and the temperature and the timing, of course that SaO2 will be great. Okay, and followed by that, some design, extract design parameters is there. Okay, like gate oxide thickness. Okay. Okay. So this is a special syntax. So extract name. Okay. So name is a user defined name, any name you can give. And the thickness is a special statement, and oxide. So which material you want to check it. Okay. And followed by that, you are taking one line or the X value at 0.05 X line. What is your thickness of the oxide? Okay. So it will display it in the variable history. Okay. So let me just run it. Okay, so you can see here it's around 100 microns. The thickness of the gate oxide is 100 microns. It will be displayed in the variable history. And so let me plot this in Tony plot. Okay, so you can see here. So it will be around, it will be 100 microns. Okay. So every time you no need to check it from the structure, you can directly use this extract parameters. So there are different parameters are there to calculate with. You can check it with commands, syntax dialogues, and extract dialog. And so here two things are there, like process extract and device extract. So here I'm going to use process extract. Okay. So you can use material thickness, junction, surface concentration. Okay, so almost everything like SIMS profile, sheet resistance, conductivity. So all those things you can check. Okay, and so the material you have used. Okay, so different materials. Okay, so you can write it here. Let's say you used oxide, and you can write it here as oxide. And you want to check some different material you have added, so that you can include. Okay, and user defined materials also it's available. Okay, if you tick mark the user defined material and you add your user defined material, so you can check its material thickness and different parameters. Okay, so let me close this. So now we'll do one experimental thing. Let's say for 925 temperature at the 11 minutes, our gate oxide is around 100 microns dot 100 microns. So what will happen if the time will be increased around 30 minutes? Okay. So you just remember this 100 microns. Let me run this and show you the thickness it varies or not. Okay, so you can see here. Okay, the temperature and dry O2. Okay, is exposed for almost half of the time before. So due to that, the gate oxide thickness has been introduced to 196 microns. Okay, so likewise you can change the different parameters, like so 11 minutes means so it will be around 100 microns. Okay, so what will happen if the temperature will be 1200? Okay, so let's see about that. Okay, so you can see due to this increasing the temperature, so it went around 1000 microns. Okay, 993, it came around 1000 microns. Okay, so let me just plot the structure also, you can get a better visualization. Okay, so you can see the difference. Okay, so let me revert back to what it is. So now we'll move to the next step, which is VT adjust implant. So we are going to give a doping profile inside, which is a boron doping profile. Okay, so let's do that also. So this syntax we already know, like the implantation in the previous step, we have seen this. Okay, so implantation of boron, we have seen it. So now it will be done like implantation of boron at the dosage of 9.5 e power 11. Okay, and followed by that, we are depositing a polysilicon. Okay, so the polysilicon will be act as a gate electrode, so that I'm going to deposit. Okay, so let me just put that also. Okay, so let me run this. So from this step, what will happen is, so the silicon is there and SaO2 is there, and we made some doping profiles, okay, of boron, and we have added a polysilicon and another extra material here, so that we'll see about that. Okay, so let me just so I think it was simulated, and let me open the structure, which is new one. Okay, so you can see here the boron doping profiles. Okay, so it was been added, okay, around so 1 e power 18, and also you have deposited the polysilicon above the SaO2. Okay, so we have seen this structure, what it shows, it's completely in one-dimensional. So now, yeah, from this point, we'll convert this structure into two-dimensional. Okay, so for that, you are just including the axis. Okay. Okay, so as it says, from now on, the situation is two-dimensional. Okay, so you are including this p dot x. So what will happen is, if you include this p dot x, so it will take the p dot y as 0. Okay, at maximum. Okay, so which will be considered as x and y. So now the structure will be converted into two-dimensional. Okay. So let me run this. Okay, the simulation has been done. So let me open this new structure. You can see here, okay, So it's in one dimensional in left side, and right hand side it's a two dimensional. And so previously you have remembered we have given some meshing. Okay, the x will be around 0 to 6 and the y will be around 0 to 0 0.8. So those dimensions it has taken it. Okay, and also you can see so I'm just creating a off of the structure. Okay, so why I'm doing this is I'm going to mirror it to right hand side and top, bottom, and every mirroring option I'm going to choose. So by this way, you can efficiently save the timing. Okay, time of your work. Okay, so now so here what happened is if you just deposit the polysilicon, it will be like completely polysilicon. Okay, and you are removing some of the layers like polysilicon, polysilicon, which is left hand side up to this point 0.35. From x will be 0 to 0.35. What are the points will be there which will be removed? Okay, so you can see here, let me zoom here and show you from 0 to 0.35, what are the polysilicon is there, which it will just etched out, which is removed. Okay, so this is what the syntax is. The followed by that, so we are going to perform stress and strain simulation. Okay, so for that, since the simulator will be simulated using physical models, we are including some physical models. So for that method and Fermi compress method I'm going to use. Okay, for that Fermi and compress. Okay, so the compress, what it will do is it will compress, it will put some compression profile in your structure. Okay, along with that you are including this diffusion. Okay, so diffusion we all know, like you are including some temperature and time with along with some different uh, like different gas like oxygen or nitrogen. Okay, so let me just put this and show you how the structure due to stress has been changed out. Okay, so let me run this. Okay, so it was done. So this is what the previous structure is. So let me just show you. Due to stress, what will happen is the device is kind of stressed out. Stress. So some stress is will be included. You can see here. Here there is no stress. It's kind of sharp in everywhere. Okay. So due to stress, you can see here some the structural changes has been changed. Okay, so this type of okay, so if you change a different stress, it will change accordingly. Okay, and due to this diffusion, the the oxidation has been performed. The top layer, that SiO2 has been formed. Okay, so let me go to the next step. So we are going to include this phosphorus doping. So we want these channels like N channel and P channel should be formed. Okay, for that implanting the phosphorus here. Okay, so implanting the phosphorus. Let me just run and show you the phosphorus, how it has been implanted. Okay. Okay, so in the right hand side and left hand side, I'm showing you different things. In the left hand side, we haven't done any phosphorus implantation. You can see here the doping profile, how it is. In the right hand side, you can see we have made a phosphorus doping. You can see how the active phosphorus has been deposited. Okay, so which forms basically an N channel. Okay. So let me go to the next step, which is so depositing the oxide. Okay, so it has an oxide is there. So if you deposit an oxide, the oxide layer will get thickened. Okay, so more oxide will be deposited in the top of it. So the thickness of 0.12 microns, and the division is for the meshing conditions. Meshing will be division at 8, so the different triangles will be formed accordingly. Okay, so let me just show you. So let me run this. Okay, so you can see here. Okay, so due to this oxide, uh, uh, plus 0.12 has been added in this region. Okay, so now moving to the next step is, so we are going to remove this. So why we are depositing extra SiO2 and again etching the same SiO2 is, so we already discussed about the sacrificial cleaning oxide for that purpose, to remove any impurities in the top layer. Okay, so it will just remove, and followed by that arsenic doping profiles and some component statement. Okay, so let me just put this here. I am not simulated. Let me just open this previously simulated what happened. Okay, so you can see here in the top, we made this extra 120 microns, and now it was removed. Okay, from the top view, you can see here 0.12 microns will be removed. Okay, due to the etch statement. So now, followed by that, so we have added some already the phosphorus doping has been added. Now we will do this arsenic doping profile, and along with this some compress models with the temperature, diffusion temperatures, temperature at 900 and time at 1 minute, and uses nitrogen gas. Okay, so let's just run it. Okay, let me just remove this one. Okay, so now, so let me show you the doping profile of the both. Okay, so I'm choosing net doping here. Okay, and here also I'm choosing the net doping. Okay, so you can see there is a difference in the doping profile here in the gate oxide. So it's kind of it's not even in this area. So due to this diffusion and doping profile adding, you can see the difference. Okay, so let me go to the next step is, so here, so we have made this channel gate oxide and gate metal, and we have made this doping profile also. So let me show you the channel also, I think so. Like, so again, this doping profile. Okay, it is net doping. And if you go to display, you can see here this violet colored, purple color one. So which is a P type, you can see here in detail, and the red color will be around N type. Okay, so these are two regions which will form a junction in this area. Okay, so this junction you can see. Okay, like you can go to display, and I think previous session we have seen all those things. So this is what the junction it is. You just click it here, and if you give apply, you can see the junction. Okay, one line is there, right? So this is the junction between N type and P type. Okay, and you can see different meshing parameters and all those things if you wanted. So now let me go to the next step. Yes. Okay, so here, so we made a gate oxide completely. Okay, so now we want to make a source electrode. Okay, so for that, to make the source electrode, we should remove this oxide. Okay, this oxide like around 0 to 0.22 something like that, we should remove. Then we implant an aluminum contacts in that. Okay, so for that, what we'll do is, okay, we use this etch statement. So etch oxide left side until the x point 0 to 0.18, whatever the oxide is there, which will be removed. Okay, so just simulating it. So this is the previous structure. Let me open the new one. Okay, so you can see here exactly 0.18, whatever the oxide is there, which will be removed. Okay, so it shows uh, the channel, the silicon blank. So now we'll deposit an aluminum over it to form source or drain electrodes. Okay, so we can directly write. Okay, so depositing the aluminum at the thickness of 30 nanometers. Okay, so the aluminum will be deposited above that. Okay, it was simulated. So let me open it. So you can see in the top layer, the completely and aluminum has been deposited. So now we'll remove unwanted aluminum in the top. Okay, so just we want some 0.18 up to 0.18 we want. After that, we don't want anything. Okay, so what we'll do is we use this etch statement. Okay. Okay, so etch aluminum. So before it, we can see the left hand side. Now it's right hand side. And from the point 0.18, whatever the aluminum is there will be removed. Okay, so let me just show you. Let me plot this. Okay, so you can see here, whatever the excess aluminum, unwanted aluminum will be removed.
Hello.
Yes.
Yes, sir. Can we remove the aluminum or whatever else in some ranges?
Yeah, you can choose. You can choose. Okay, so let's say. So I'll just remove this statement. So I just comment this statement. So I'm directly going to the command. Okay, and process dialog. and I'm selecting the process etch. Okay. So I think okay, so geometry is there and etch machine is there. Okay, so etch machine means what it is so I think my voice is echoing. Can
Okay,
you
okay.
mute it? Okay, so etch method is there. Geometry means you include the points to remove it. Okay, and the etch machine means accordingly based on the fabricator. Okay, uh, different factors are there, accordingly it will remove. Okay, so geometric condition I'm choosing, and geometric type all, and the material I'm choosing is aluminum. Okay, so aluminum is the top layer, I want to remove it. And you can choose so what like right side, left side, above part or below part. Okay, and dry thickness means like the thickness you want to remove. Okay, and any shape if you give, and you can insert the points. Okay, so let's say from 0 to 0.1 I want to remove. Okay, at the x value. Okay, so for that uh, you can give 0 and insert, and so you need to choose the location correctly. Okay, so let me just zoom in. Y will be 0.22. Okay, so let me delete this 0 and 0.22 and insert, and so the next point will be around, let me check, 0.1. Okay, and the same location I want to remove. Okay, and you just click here and give right. Okay, so it will choose the point. Okay, etch aluminum. Okay, the starts with x 0 to 0.22, whatever the things, it will be removed. Okay, and etch, and it will be done. It's completing the statement. Let me run this and show you. So here I just commented this statement. So the aluminum will be the completely covered situation. Let me just show you that. Okay, so it's completely covered. Let me just remove this one and show you. What is this? Okay, so this is edge. So let's say we can give this edge and E1 dot x equal to 0, and P2 dot x equal to about this syntax. Until 0.2 is it? Okay, I think I'll give 0.1. Okay, so likewise you can choose accordingly. So just removing everything. Okay, so it will be left until 0. Okay, so you can see here. So this is what the syntax it is for removing like this. Okay, so like this you can remove. So let me just remove the statement. So different points also is possible. And followed by that, so here I just made everything. Hello?
Hello.
Okay. Yes, yes.
Yeah, it's okay.
So let me undo this, whatever changes I have done. So now the structure mirroring I'm going to do. Structure mirror right. Okay, so here, so let me show you the structure until it was created. Only right hand side part is been created. Sorry, left hand side part is been created. So everything is done. Okay, we just mirror it to make the complete structure. Okay, so for that structure mirror right. Okay, there is a command for this also, and for that is mirroring. Okay, so you can use like stretching, and you can use relax means it's kind of squeezing your structure. Okay, and mirroring and adding electrodes. Okay, these are the different function which is available. Okay, and here's the structure mirror right hand side will just, so let me just run it. Whatever things which is present in the right hand side, it will be mirrored to the left hand side to right hand side. It's not created yet. Let me just wait for it. Okay, it's done now. Okay, so you can see here only half of the structure we have created and just mirror it, and we make a complete structure. So this saves lots of time. Everything will be mirrored. Let me show you the doping profile also. So it forms this N, P, and N. Okay, two regions, and everything will be mirrored. Okay, or else if you want, you can uh, create the complete structure from the beginning also. I'm just giving you the features, one of the feature in Athena. Okay. Followed by that, I'm just going to mirror this to bottom also, and to get how the dual gate structure. Okay, structure, so mirror bottom. Okay, so let's run this. Okay, so you can see here it's a kind of dual gate device. Okay, you can just mirror it out. Okay, so you have made only half of the structure and you made a complete structure. Okay, let's say to creating this half of the structure, it takes around half an hour, and for the full structure, no, it will take lots of time. So here the time will be saved a lot. Okay, so around 3 times the time will be saved. Okay, as usual as everything, like you can choose the doping profile also, everything will be mirrored out. Okay, so let me go to the next step is, so here I have defined that electrodes like source, drain, this metal, only the aluminum metal and polysilicon metal is been chosen out. Okay, so now we are going to name it. Okay, so for that, electrode name will be gate and the point. Okay, so the gate will be like, let me show you. X will be 0.5 and Y will be 0.1. Okay, so X will be 0.5 and Y will be 0.1. Okay, the intersection point, right? 0.5 and 0.5, the intersection point, whatever the region will be there, will be represent as gate. Okay, and as usual goes for source, okay, and drain. Okay, the source will be X will be 0.1, and if you didn't give Y, it will take it as 0. Okay, and as usual goes for the drain. Okay, so 0.1 means it will be comes to here. So at this point you can see one line, you can think of it, and you haven't defined uh, y axis. So the y axis, if you haven't defined default, it will take 0, and you can see here in default there is no region in 0. So what will happen is it will take the minimum region where it's present. Okay, so which will be around 0.22. Okay, it will choose this region as a source, and as well as like 1.1, it will choose this region as a drain. Okay, so let me just put this. So substrate, so I'm going to define this in the bottom of that. Okay, as a substrate, as we are giving it as a backside. Okay, and this different syntax is there, like top, bottom, right, left. Okay, so all those syntax also you can use it here. Okay, let me just put this and show you. Okay, let me run this. Okay, so why we are naming this is, okay, in the after the structure simulation, so we need to do some solution solving using physical model. For that we need to name it, like name it as gate, source, drain, electrodes. Then we can ramp some voltage in the gate voltage and perform this output or transfer characteristics. Okay, so for that reason only. Okay, so let me just plot this, the structure. So it's the same thing, and let me just go to the display, and now there is one uh, uh, button called electrodes. If you select this electrode and give apply, you can see so where that electrode has been named. Okay, so this region has been named as source, gate, and drain. Okay, so if you have any doubts, you just ask me from this here. Okay, if you have any doubts, do let me know now. So I hope, hello?
Yeah, please proceed.
Yes.
I think, just
Yes,
check
sure.
if someone asks any question and then we can proceed.
Yes, so let me check with the.
Okay. No question in chat.
Okay, no questions, is it?
Yeah. Okay, then, so Dr. Gopal, you're there. So we are almost done with the morning session.
Yeah, I'm here only.
Yes. So if anyone have any doubt with respect to what engine I've discussed so far, they can get it clarified, because in the afternoon session, we are going to see how to characterize the device which engine I've created using the various fabrication steps. And then we'll be proceeding how to create a structure using with respect to the device simulator and characterize it. And we'll be moving on with visualizing or creating the family of curves. and followed with mixed mode simulation. So if they have any doubt with respect to Athena, the process simulator, I think we can just spend another 5 more minutes to get it done, and then we'll go for the lunch break.
Yes, Engine, I think you can also tell us about the access to library, like where they can find some examples related to Athena itself.
Yes, sure, sir. So let me open a new one. So new Deckbuild. Okay. Okay. So let's say this is a so initial case, initial thing you launch the Deckbuild, and you want to let me just save this in a different folder at the beginning. Okay, so let me just create a new folder. Okay, and you can save it anything like demo 1 or something like that, and save. Okay, so now you can go to file and examples, and two things are there: examples and examples in browser. So if you give examples in browser, it will launch in Firefox or Chrome browser. Okay, and you can choose in examples. Okay, so in the examples you can find a different at the beginning 3 folder: technology, product, and solid modeling. Okay, so the technology based categorized, it will be categorized into 3. Okay, let's say based on the technology like BJT. Okay, and CCT, diode. Okay, so like if you are working in a selected topic like MOSFET, LED. Okay, so it will be categorized in folders. Okay, so let's say you are working in MOSFET. Okay, so the MOSFET contains 2 folders. Okay, MOSFET 1 and MOSFET 2. So MOSFET 1, which will show the basics of MOSFET simulations, and MOS 2, which contains advanced MOS simulations. Okay, for advanced applications. If you just uh, expand this, so you can find a different things they have mentioned it. Okay, the first example they done it for to calculate this IDVG and the threshold voltage calculations. Okay, and then IDVDS calculations. Okay, IDVDS curve and subthreshold slope, how it's been done, and how debill extraction is being done. Okay, the body effect extraction. So all those things you can do. So let's say the first one I have taken it. So let me just maximize this window, and in the bottom you can see so what this example contains. Okay, so in the heading itself you can see ID and VG. Okay, so they are basically calculating the uh, transfer characteristics, and they also checking the threshold voltage. Okay, so how the check what is the threshold voltage of the device, and for that the minimum requirement is Supreme 4 and Spice, and the minimum version should be Athena and Atlas accordingly. Okay, so this is the structure which they use. The same structure I have created it. Okay, and if you just drag it down, so they will be displaying the output characteristic, which is IDVG. Okay, so which will be displayed here, the drain current versus gate voltage. Okay, so the graph you can visualize directly, and followed by that, so they will be given the complete explanation of how they have done. Okay, like basic MOSFET in Atlas. Okay, the process simulation of MOS characteristic in Athena, and the process parameters. Okay, oxide thickness and on all those stuffs. And they use this auto interface between Athena and Atlas. So what they have done is they created a structure in Athena, and they getting electrical parameters is IDVG in Atlas. Okay, and to extract this IDVG curve, when your drain voltage at 0.1 volt, and extraction parameters like VT, okay, linear gain and mobility roll off, all those conditions. Okay, so in this thing, there is some special statements will be there. So all those special statements, they will be declared. So okay, so initially meshing and the region creation, okay, and the interactive tools, okay, and the models they use, and all those things they will be explained in detail. Okay, to to see the code in this environment is, so you just need to give load. Okay, if you give load, it will be extracted in this thing. Okay, so go Athena, and followed by that the complete statement what we have seen here. Okay, so here they have done some extract statements like for extracting the junction, N junction. What is the N junction? Okay, N plus plus region as sheet resistance. Okay, and different curves like the conductance curve, surface conductance curve. So all those things they have made the extraction. Okay, and finally they go for this. So IDVG characteristics. Okay, so they go for Atlas. Okay, and followed by that some models and some parameters like work functions, interface, and methods, solve, initialize. And so drain voltage they're setting at 0.1 volt, and they're ramping at gate voltage at 0 to 3 volt. Okay, and so due to this ramping, how your output will be changed. So everything, this code will be checked in detail in afternoon session. Okay, so I hope this is the procedure to take the from examples to you can learn from this example a lot. Okay, so any doubts on this?
Hello.
Hello.
Hello. Yes, sir. This is all about if you have any example, then we can easily load it.
Yes.
If, for example, we need to go for the new structure kind of things.
Okay. Okay.
So
So
what we need to do in that?
so if you are going to create a new structure, okay,
Yeah.
so that's what so we are going to teach in the afternoon session, how to create the structure. Okay, and how to create from the scratch, and everything we'll discuss in the afternoon session. Okay, so it's kind of around 1 hour at 1.5 hour process, so we will explain you in detail in that.
Okay, sir.
Okay, so anything else?
I think you can go for a break and resume back. It's already 1:10.
Okay, okay, sure.
With a specific material that is available in the Atlas library. So regions are like it will be created with like I can give a material of say about silicon. I can create a region number 1 for silicon, region number 2 for aluminum, region number 3 for silicon dioxide, etc. Any number of regions can be created. And the third one is electrode. So electrode, we have already seen in the previous morning session, electrode that was generated in Athena. So electrodes can be defined either in the process simulator, or if you are creating a structure using device simulator, then electrode can be defined in the device simulator directly. So electrodes specify the location and the names of electrodes in the previously defined mesh. So this location can be of any specific region, or like a pair of cathode or anode electrodes. So it can be for different applications like on which we are working with. And then we have doping as a last statement in structure specification. So doping, as we know, it specify the doping profile in a device structure, either analytically or from the input file. So the next category is material model specification. So after defining the basic structure specification, we are moving on with providing the tool with the material and the model specification. So under this category, the statements are material, models, contact, and interfaces. So material, we know like what kind of material we are working with. And this is like it's a previously defined and doped region that must be provided with some specific material. So these material, their property, their physical parameters, everything will be automatically selected from the Atlas database among a number of elements, compounds, and alloys. So the user specify the material and its property using like I can show the format a little later. So using those format, we can directly specify the properties of the material, particular material in the material statement. Next is model statement. So model, the like once we define with the mesh, once we define with the geometry and provided with the doping profiles, we can modify the characteristic of the electrodes, or we can change the default material parameters, and then we can choose which physical models that Atlas will be using during the device simulation. So the physical models, generally it will be grouped into like 5 in Silvaco TCAD. That is, it will be categorized into 5, which includes the mobility model, recombination model, carrier statistics, impact ionization, and tunneling. So like we can like during demonstration, we will try to show you how these models are being categorized in Silvaco TCAD Atlas. Next is about contact. Yeah, so you have defined the electrode. If you want to perform or if you want to provide with the work function for the particular electrode which you have defined, you can call the same electrode and you can provide the work function for the same. Then interface, like if you would like to provide the charge, interface charges between our semiconductor and insulator. So in that case, you would like to provide those values, then it should be defined by means of using interface statement. After the structure specification and after the material and model specification, the next category is numerical method selection. There are a number of methods that is available in Silvaco TCAD. This is basically I can call it as a solution method. So numerical methods will be helpful for solving the equations and the parameters that are associated with like algorithms that we generally define by means of using method statement. So as I mentioned earlier, there are several numerical methods are like available in this Atlas library, and I would like to specify 3 major types, like Gummel method, Newton method, block method. So these 3 are like the most important or main types of method that is required for any simulation purpose in the device simulator. So Gummel method is just like I can say it's a like a very weakly coupled system equation. So if we are going for a solution for a weakly coupled system equations, it is it provides with only linear convergence. Newton method is a strongly coupled system equation. It is provided with a quadratic convergence. So it requires the Atlas to spend more time solving for quantities which are essentially constant or weakly coupled. So we prefer this method mainly to obtain and ensure convergence and a more accurate approximation that is needed from the system. Apart from that, block method is that is like faster solution when the Newton method is like if it is not in a position to provide a reliable solution, then in that case block methods are being preferred. Okay, now after these 3 categories, the next definition that should be made in the device simulator is a solution specification, under which we have like log statement, solve statement, load statement, save statement. So we'll be quickly just in another 5 or 10 minutes, we'll be looking into it, how these are being called into the device simulator. So Atlas, as I mentioned, like it is a tool which is required to perform any electrical behavior, to analyze any electrical behavior, thermal behavior, optical behavior of a device. So it can calculate the DC, AC, and transient solution. So Obtaining solution is like something similar to setting up a parametric test equipment for a device test. So the user usually defines the voltages on each electrode in the device, and then Atlas calculates the current through each electrode and the internal quantities, like I can say the carrier concentration, electric fields throughout the device. So in all the simulations, the device will be starting with a zero bias on all electrodes. So solutions are obtained by stepping the biases on electrodes like from the initial equilibrium condition. So to obtain conversion for the equation used, the user should apply a good initial guess for the variables to be evaluated at each bias point. So Atlas solver uses the initial guess and it iterates to be converged solution. So solution, it is divided into 4 parts, has been given here: log, solve, and then load, and then save file. So these are the terminal characteristic that is being used to, they store the terminal characteristic that is calculated by the Atlas. So while we go in depth about like understanding the scripting, I'll explain each and every line. Then about the last group is about the result analysis, where you have two statements, that is extract and tonic. So before the solution specification, you would have ramped the voltages and you would have obtained either a transfer characteristic or output characteristic, or you're going for any AC simulations. All these plots you would have obtained. Like CV characteristics, all these have been obtained. Okay, now if I want to extract a particular parameter from the curve, in that case, I need to go for an extract statement. So as I mentioned earlier, if you want to extract an say about a transconductance from the IDVG curve, or you want to obtain a subthreshold slope, or you want to analyze the threshold voltage, extract the value of the threshold voltage from the curve. There are so many parameters we generally extract, right? So all these parameters can be obtained by means of using extract statement. And the last one, the last statement in the result analysis is the tonic plot. That is, we have created a structure, we have undergone meshing, region creation, electrode definition, doping, giving the region with a different material, providing a physical model, creating a contact with the work function, and going for a method selection, solving or ramping the voltage, and we have obtained the curve. And the particular curve which we have saved, if we want to view, you need to go to the tonic plot. Or if you want to view the structure you have created, then you need to include the statement called tonic plot. So this is all about the device structure creation and simulation. The flow, it should be in the same manner. And for example, okay, first step, as the first and foremost step, if I go for using method statement, and then I go for structure specification, that will not be taken by the two. So the flow is first go for structure specification, followed with material and model. Third is what the numerical method. So you can't go for interchanging these groups. So this I want to specify. Moving on further. This is about like the comments, the statements that we define, syntax, basically syntax. How do we define mesh? And then how do we define a region statement in a scripting? So the mesh will be in the case of Atlas, the device simulator, it will be x.mesh, y.mesh. So x.mesh specifies the meshing in the x direction, and y.mesh specifies the mesh in the y direction. And if suppose, if you are working with the 3D structure in the device simulator Atlas, in that case, you will be referring to the z.mesh. So it will be z.mesh. And the location means like which location in the x direction you want this mesh to start with, and the spacing, that is from one neighboring point to another neighboring point in the x direction, what should be the spacing value. So by default, it will be in micrometers. So by default in TCAD, everything will be in micrometers. So whatever the inputs you give, you make sure that you're converting it to like if you're working with nano, if you're working with micro, it's fine, default, not an issue. But if you're working with nano, then accordingly the conversion should be made. Yes, so the next is about region statement. So you, for defining a region, first you need to give the statement, and then number, region number 1, region number 2, region number 3. So we are giving the number for the region what we have created. Material, what type of material it is. Is it a silicon, or it is a silicon germanium, or you are going for a GaN? Whatever the material that is available in Silvaco TCAD can be presented over here. And position. So in X direction, this region should be formed from the particular location of X minimum to a X maximum value. And in the similarly, the region should form this material in the Y direction from Y minimum to Y maximum. So all these specifications will be provided in the region statement. Next is defining the electrode and doping. So the format is electrode statement, name of the electrode, and the position. Like again, if it is a two-dimensional X and Y position of the electrode, you can specify it over here. Next is about doping. Doping, the statement is doping, distribution type, either uniform doping or you're going for a Gaussian doping. If it is an N type or a P type, so you specify it as dopant type. And again, the position parameters. So which either doping is like possible of giving region wise, material wise, okay, or for the entire device. So if you're going for entire device, you are giving a position parameters. If you're going for a particular specific region, for the doping of say uniform of N-type doping. So in that case, you provide the X and Y direction. You're being very specific to the region where you need to apply the doping. Next is about material and solution specification. The statement is material, and then you go for material definition, like either it is a like you just mentioned, whether it is a what type of material, it's a silicon material or a compound material, you specify that. Along with that, you provide the basic properties of that particular material. So here is an example. So material statement, name of the material, so which is equal to, that is material equal to silicon here. And then you define the band gap of the particular material, permittivity, affinity, and then you go for the lifetime carriers, specifying the lifetime carriers, everything in the material statement. And the next solution specification is like saving of file. So in that case, you have the statement called log as a statement, out F, that is you're going to output the file, and the file name is of user defined file name. So this is what in solution specification. So once I show the demo, I'll just give much more clear explanation about this log. And then physics models, as quite aware, there are lots and lots of physics models are used using the models and the impact statement. So as I mentioned earlier, it is categorized into how do we define our models into the device simulator is like either using model statement, or you can use the impact. If it is a mobility model, you can use the statement mobility. If you are in the material also, you can define it. Material wise also, you can define the model. So you can be very specific. This particular model should be applied for this particular material as well, specific material. So in that case, yes, that is also possible by means of definition in the device simulator atlas. Now, as I mentioned earlier, it is grouped into 5 categories. So mobility, recombination, carrier statistic, impact ionization, and tunneling models. So the statement syntax is like models followed with the model name. So this is a basic overview of the flow or the pattern that we generally follow while creating a characterizing or we're creating or characterizing any device using the device simulator atlas. So without any delay, let me just quickly move on with showing a definition. Okay, so this is what I think morning engine discussed about the structure creation that is undergoing a various fabrication steps using the process simulator Athena. So I've just used the same structure, but how do we characterize this structure? Or in other terms, I can say, I've created the structure using Athena, but how do I directly take into the other framework, that is Atlas, for biasing and then performing the solution perspective? So in that case, this is the structure that's been created using Athena. And now we can just go for including the device simulator, that is calling the device simulator in the Deckbuild platform. So to perform that, we use the term called Go Atlas. Okay. So first we have used Go Atlas. So I remember that I told you, like, see, if you're starting the simulation, let me just quit here and I'll show you. So if I just start the simulation, so this particular data will be simulated and it will be saved. So this structure is right now saved. As you could see, it is saved in the runtime output. Now, every time is it necessary for me to run from the initial line? It is not the case. So once if you have no modification with respect to your structure that's been created using Athena, what you can do is you can click on the line where you want to simulate, and you can either give right click and give go to line, or you can just click this icon which is called go to line, so that keeping in that particular line, you could see that this line has been highlighted right now. So after keeping in this line, you can start your simulation. So the simulation starts from the line where I have selected. Okay. So now I'll just give a brief overview of what happens when Go Atlas particular line simulates. So this, when you simulate this Go Atlas line, it will start, when you simulate it, it will show you the Atlas framework is being called into this Deckbuild framework. Deckbuild platform, and you could see what version of Atlas you are using, and then what are the modules that is being enabled. This depends upon user to user. So what are all the modules that are available will be displayed over here. You can check whether it is enabled. Okay, so this particular thing shows all the module that is available in Atlas and whether it is enabled or disabled for you. So with this, you can easily have a check with this particular module is working for you. Next, we have this second line, which is the contact. So this case, you could see, I'm not creating any region. I'm not creating any mesh in the device simulator because I'm just characterizing the device which is already been processed using the process simulator Athena. So I'm going to interconnect. I'm going to interconnect this structure created using Athena. I'm taking forward to Atlas only for characterization. So I'm not creating any device using Atlas here, but I have just taken the structure because I have already told, like, just a second. So I have already told the input could be the input to the Atlas simulator can be a structure file from Athena and Deckbuild it, or a command file. Right now we are saying that as input to the device simulator is from the Athena. That is, we have taken the structure file and we are feeding into the Atlas, the device simulator, for characterization. So that is the region. That is the reason I haven't gone for the region specifications or electrode specification, because I have already defined the electrode in the Athena, created the structure, everything is ready. I need to give the work function for the electrode. So that is a contact statement. Name of the electrode. So in this case, name is gate, and end poly. So by default, if I give end dot poly, it will be taking the work function of 4.17 electron volt. Okay. Alternatively, what if, like, I'm working on like I'm specifying some other work function? So in that case, you can specify the work function as 4.1. I'll just show the first, the previous line. What happens if it is n poly? Then I will change it. I'll just relate it. Okay, so this line, I'll go here. Yes. Okay, so we could see the electrode, it has taken this is the starting of the Atlas. So it has taken the structure. So automatically it has in file, it has called the structure file mos_0.str, and it has specified how many, these are the grid points we call it as. So that is, we have defined the mesh in the Athena itself. So that is initial stage itself. We would have mentioned line X, that is X direction, and Y direction. We have mentioned the mesh. Same mesh is being carried forward to the atlas. No change in the mesh. So yeah, so it is taking the same mesh grid points followed with the same electrode that's been defined in Athena. Now we are just moving on. It just shows the geometry in which, like from which point in the X and Y direction this gate is being formed, source is being formed. So all these geometrical specification of all the electrodes has been displayed here, followed with this line of contact. So contact name N poly. So in this case, when I specify contact name as N poly, automatically it considers the value of the N poly to be 4.17 electron volt. Okay, so that's what been specified over here. If not, if I'm alternately going for specifying the work function, so in that is also possible. So in that case, I just remove this and just provide it as work function or work F, or just simply as work. That is the syntax. Or you can define for, like, for example, 4.1. So let me just simulate the same. Okay. Okay, so we could see, yeah, again, you can see the work function you have defined as 4.1. So right now it will take the work function to be 4.1, and then it will start working for that particular work function. So either you can give it as N dot poly, where the work function will be considered as 4.17 electron volt as a default, or you can specify the value of the work function here at this point. So that is what the meaning is about. And yeah, you could see the other details we'll discuss one by one. And next line is interface. That's what I told. If you are including an interface charge between your semiconductor and insulator, you can define it by means of using the interface statement. And the charge value here, in this case, it is 3^10. And that will also be taken into consideration. Next, about defining the models. So you go for the Lombardi model. This is a MOSFET. So CVT model, the Lombardi model is CVT model here. SRF, the recombination model. And then since we have a different method being specified over here, we specify this number carrier, but I can just replace and just simulate with the basic Newton model. I think that would be fine. Yeah. So this is a Newton model. And then there, as I mentioned, there are several models available in Silvaco TCAD. The preferred one is the Newton model. So here in this model statement, we specify all the models. And if you give print option, the models will be printed here in this runtime output. As you could see, this is providing with the CVT model. Okay, and then if you are giving SRH, then SRH will be specified over here, or whatever the models we define will be specified in this runtime output. So you could see yeah, there are so many. You could see, like, using field mobility model, and then there are a number of models available. So in this case, we have used CVT and the SRH model. Method to solve the equation is Newton method. It's been selected. Every time after the declaration of method statement, we go for the solve statement. So in solve statement, every time we have an initial guess. So initial guess is always performed with the Gumbel method. So once after the Gumbel method is done, the solution make sure that there is no convergence when we move on with the next biasing point. So in this case, initial guess will be performed. I'll just quickly show. We got simulator. Okay, this. So this is what the Gumbel, M means the method, Gumbel method. So initial guess is done. So now the device is ready for performing the solution for various biasing conditions that we provide. So in this case, solve statement, that is for a gate voltage of 1.1 volt, we need to solve the statement using the method Newton. Okay, So, and for the models of what we have defined, that is CVT and SRH, that is the meaning. So, solve statement, V gate, it specify the voltage of the gate. Okay, like let us see what happens when, how it affects the syntax. Just a second. Yeah, could you see? If I give the syntax wrongly, then this will show that it is an invalid parameter specification. So by means of that, we can, it will also show at which line, which one is invalid parameter. So it will help us to easily fix our errors. So this is one kind of error that we generally obtain. So it should be V gate, that is gate voltage, which is of 1.1, and by default it is in volts. Then it is about like, okay, now I have fixed a gate voltage to 1.1 volt, and I'm having a plan of ramping my drain voltage. That is, it is basically a output characteristic, IDVD characteristic. So in that case, if I'm going to ramp this voltage, okay, before that, and I'm going to save it in a log file that should be viewable, visualized using the tool Tony plot, then in that case, before ramping the voltage, we need to create the log file. So it includes the log statement followed with the outf command, that is output file command, followed with the user file name, user defined file name, should be saved with an extension of .log. So log is the statement, output f is the file name, which is a user defined file name with an extension of .log. So this should be every time should be defined before the voltage that we need to ramp. Okay, we are going to sweep. Okay, only then the values that we are sweeping will be saved in this log file. So that is the meaning. So if suppose if this log file, if you are not providing it over here, even if you ramp, the solution will be solvable, no convergence, everything is fine, but you cannot see the data in the log file. In order to visualize it as a plot, then in that case, we need to save this log file, or we need to define this log file before the solve statement of the ramping voltage. Now, moving on with this drain voltage ramping. So again, solve statement, name of the electrode or the contact that we have defined. And then V drain, as I mentioned, it is a drain voltage. So initially it is 0. V final means, so I have started my ramping from 0 and it should continue until it reaches 3.3 volt with a step of 0.3 volt, which means first value it will consider as 0, second value is 0.3, third value is 0.6. So it will be incremented by 0.3 volt, and this sweeping continues until the like it reaches a final voltage of 3.3 volt. So we are here in this case, we are sweeping the drain, and that's the reason why we gave the name as drain over here. That is, we are sweeping the drain voltage. So all these values which we have ramped will be saved in this mos_1.log file. Now, after this, we can like once our ID, this curve will be created. So after this curve is created, you can extract this. I'll just comment it. So I'll give you a different code for the same. So from this IDVD characteristic, what is my maximum drain current? So this is again a extract command. That is the statement followed with name. Name is again user defined name. It could be of, you can give I maximum or IDS maximum, that's up to the user. You can give user defined name. So max means maximum. I dot means I is representing current here. So I dot drain, that is drain current, the maximum drain current to be extracted from the curve. That is the meaning. And after this extract statement, the last and final statement, what we have is the Tony plot. So Tony plot is to visualize our plot that we have obtained. Not only plot, the structure also be parallelly viewed in Tony plot. So to define that, we call the statement Tony plot along with the log file name, which where this ramping data have been stored. So if you change this log file name, then this Tony plot will not open. I'll definitely change the name and I'll show it for you. So right now, let me simulate it. And yeah, this let me clear this output window. Oh, yes, so let me start from the initial. So it has undergone a device creation using Athena, and then it has gone for a gate voltage fixation of 1.1 volt, and drain is being swept from 0 to 3.3 volt. And once again, first I'll explain this, then I'll explain the curve characteristic. So we have ramped from 0 to 3.3. So we will check here. This is the runtime output. So we need to check. So all these are model specifications. Yeah. So solve initial. And you could see what model it has called. Since it is a basic silicon-based material device, S species is more than enough to simulate this particular device, and hence the module is being called over here. Followed with, you have the initial guess, and then we have fixed the gate voltage to be 1.1 volt. So it is ramping for the, so providing the solution for the like for these particular 1.1 volt. You could see Newton algorithm did not converge in 25 iteration. One good feature with Newton algorithm is like, once if there is a convergence, this is a convergence problem. So in that case, automatically it will reduce to smaller bias, start converging, and then resume back to the original voltage of what we hit. So 1.1 volt is what we provided. Since it could not converge, it has taken a smaller biasing condition of 0.55 volt. So it just checks whether it was able to converge. So in this case, it easily got converged. Okay, so after converging, now again it starts with the original voltage of what we have defined to be 1.1 volt. Again, if it faces the issue, then again it is reduced by one time. And until it reached the voltage of what we have given, it keeps doing it. So now we could see at the 1.1 volt, this particular like voltage has been like the current has been obtained, and this is saved in like right now we are going to perform the sweeping of the drain voltage, and which is to be saved in the dot log file, MOS_1 dot log file. And in the first case, you know, it is going to be 0. So this is for the 0 condition. Then with increment of 0.3, V step is the increment of 0.3 volt. So you could see for a 0.3 volt, it just sees whether conversion. If not, it reduces its bias, and until it obtain, it will be like sweeping it. You could see here like 3 to 4 times, but after that it obtain the volt of 0.3. So 0.15. So this is 0.3. It has converged. 0.6 next is. Next 0.9 and 0.1 to 1.2, 1.5, and it just goes until it reaches the final voltage of what we have defined, that is 3.3 volt. So after that, it stops. So 3 volt, the drain voltage is 3 volt here, and the drain voltage is 3.3 volt here. And after reaching 3.3 volt, it stops. So now that is, it moves on to the next line. That is the extract command which I have provided. And you could see from the curve, I want the maximum drain current, and that particular value is being provided over here. So this is about the statement, and then I'll just open this log file. Yeah, it's been opened here if I'm not wrong. Yeah, by default, Atlas, the device simulator, it opens the IDVG characteristics. But what we have performed IDVD characteristics. So in that case, how do we change the Y quantity or the X axis or the Y axis is right click, display. Okay, in display, X quantity, like that's what we want to change. We want it to be drain current, sorry, drain voltage. So I've selected drain voltage, and Y axis is drain current. So there is no change. So let me give apply. So this is what your IDVD characteristics of this particular device is about. And if you want to see your Y scale in log, you can take the log here. It has linear and log. Right now it is linear, and you can see the log file as well. So this is for the log of the Y axis. So this can be done. Then what else? Likewise, you can select the parameter that is available here and view it in your toning plot. Okay, so this is one such example where you characterize your device for the structure that's been created using Athena, the process simulator, and then you characterize it in the Atlas, the device simulator. Now just imagine that you are going to create a structure using the Atlas from the scratch. So in that case, first you go for the statement of go Atlas. Okay, then I'm going to define the mesh. So that is mesh in, since it's a 2D, it is x dot mesh. This is the syntax. Please understand the syntax of Athena defining the mesh will be a little different comparatively with the Atlas syntax, but need not worry, you find everything, even the basic statement of the syntax in the manual. So I will open and I'll definitely show it as well. So in this case, it is x dot mesh. As I mentioned, you should specify which location you want to start along with the spacing. So in this case, it is 0.025 micrometer, or I can say it is a 25 nanometer spacing between one point to another point. So depending upon this spacing only, the mesh grid lines will be formed. So you define the mesh in both X and Y direction. Similarly, location you will specify and the spacing you will specify. Next, after the declaration of mesh statement, the second one what we saw, it is region. Okay, so region is region statement followed with number of the statement. So if it is a region number 1, its number equivalent to 1. And this is what I told. So you need to specify the location of the region to be like you want to create in both X and Y axis. If you are using 3D, then Z axis also to be mentioned over here. So for that, the syntax is X dot minimum, the minimum X axis value, X dot maximum, the maximum X axis value, Y dot minimum, the minimum Y axis value, and Y dot maximum, the maximum Y axis value to be defined for that particular region. So the region I have defined number 1, but what is the material of the region? In that case, I can choose the material to be like anything, oxide in this case. Now, if you see the region number 2, I have selected the location in which the region to be created, and the material is silicon. And similarly, material 3, material 4. So likewise, any number of material that can be created. You could see like electrodes over here. So after this definition, we go for specifying the electrode statement. So yeah, as given here. So it is electrode. So in this case, electrode also to be provided with the position, that is in X and Y axis. So if in Atlas, very simple, in Atlas, the device simulator, if you want to specify the location or the position, then in that case, you need to use these terms: X dot minimum, X dot maximum, Y dot minimum, Y dot maximum. If you are using 3-dimensional, then Z dot minimum, Z dot maximum should also be included. So in this case, I have defined the position of my electrode, which is named as source. Then I am defining an electrode with this position along the X and Y axis with the name as gate. Then I define as electrode of the position in both X and Y axis with the name drain. And followed with, if it is going to be substrate at the bottom, just give it as bottom, do not go for specification, but still it is up to the user's point of view. And then next category is doping. So that is, right now we have seen only the structure specification. So in doping, yeah, so that's what I told. You can specify you can specify the doping region wise, position wise, or for the entire device. Okay, so if in this case, I'm giving doping for the region 2. Region 2 is what? Silicon. And this is the position. So when I specify region 2, the tool will automatically go to this line, see what is the property that we have defined, and it will apply it over here. So that's the reason why we give the region number, why we specify or define the region number. So it has gone doping statement region 2 for the region 2. For that position alone, p-type dopant is chosen and the concentration is given, where the type of doping is uniform doping. Similarly, for region 3, n-type dopant is chosen with the concentration value centimeter cube, and you can see the type to be uniform. If alternatively, if we want to specify it by the position values rather than giving region values, in that case, here we specify it by means of using x minimum, x maximum, y dot minimum, y dot maximum, followed with the same concentration, whether the type is n-type or p-type, or whether it is uniform or Gaussian, dependent. So you can specify region-wise, or you can specify position-wise, or alternatively, you can give the material-wise definition as well. So 3 possibilities are there while defining the doping statement. Now, once that is done, next we are moving on with the model statement. So model statement, as I mentioned, like this is the same simple MOS structure has been created using Atlas. So in this case, I'm choosing the same model to be CVT and SRH, method to be Newton. In this case, I would like to obtain a transfer characteristic, IDVG curve characteristic. So my first initial thing will be my initial guess. So that is solve initial. Then I will be fixing my drain voltage. So in this case, you could see very clearly, I'm fixing my drain voltage to be first I'm sweeping 0.005, and later I'm increasing to 0.05. So either you can directly give it as 0.05 volt itself, or you can step by step, you can increase your drain voltage. And then you have the log statement. So you know this, when I sweep this gate voltage, I make sure if I want to save all the data, then I need to include the log statement before the solve statement. So it is log out file, which is equivalent to, this is a user-defined file name. So MOS underscore atlas underscore 0 is a user-defined name with an extension of .log. So once this line is written, then you go for the solve statement, where you have the gate voltage that is being swept from 0.4 to the final voltage of 1 volt with the step of 0.05 volt. And the name is the gate. So the gate electrode is called here. Gate voltage is ramped from 0.4 to 1 volt with the step of 0.05 volt. That is the meaning. And from this curve characteristic, IDVG curve characteristic, we obtain the threshold value, and we know this analytical formula behind the same. So for a particular value of y value, we from the curve of I, that is V dot, that is curve, V dot gate means that gate voltage in the x-axis, I dot drain means drain current in the y-axis. And same way, if you want to obtain the leakage current, obviously leakage current is the minimum current obtained from the curve. So that's been written over here. Now, after all these performance, you want, like after biasing condition, doping condition, everything, you want to see your structure, then in that case, you save your structure, save out file, user defined file name with .str extension. So you save the structure file with .str extension. If you want to see the structure, call the Tony plot statement. If you want to see the log file, it is the data file where we have obtained a curve characteristic, then it should be viewed in the Tony plot, and we should call the log file name. Okay, now we will see some syntax problem, like what happens if you don't define the same. So in this case, if I just give it as x minimum, let us see what happens. So you could see again the invalid parameter. So you should be very careful in defining the syntax. All these syntax along with their explanation is given in the manual. So I don't think so it will be a difficult task. And here also, if I make it as y mesh, So you could see it is showing invalid parameter specification. Okay, now everything is perfect. You have done everything. You have created a structure using different region statement. You have given the electrode, you have given the doping, and then you have given the models, methods, ramped. Everything is perfect right now. Now, suppose you face with the convergence problem, okay, so in this case, it's automatically chosen, it's solved. But in some cases, it may have a hindrance. So in that case, what are the predominant factors that we need to consider in order to avoid this convergence is, first and foremost, check the meshing. That is, you can adjust the mesh spacing. Okay, so by means of reducing the mesh space. So in this case and all, it is going to be very smaller mesh, 0.005. Okay, so in this going to be, it's a very smaller mesh. So in this case, if you are going even lower mesh, even smaller spacing, this may also, that is, you're making your meshing to be very fine in a region. Like by mistake, people go for doing for the entire device. So that is not actually required at all. And because that's the reason I told, in a device, you require fine meshing for accurate results. I accept. But in the meantime, you also need a coarse mesh in order to get the device efficiency. So considering both factors, we need to make sure we give a proper meshing. So if suppose in future, while you're working with this tool and you come across a conversion issue, the first and foremost thing that we need to remember or we need to check is mesh. So you can adjust the mesh, and I'll change the mesh and I'll show you how it is having an impact on the structure. And then you need to make sure that while defining, you're giving a proper region number. So when you're calling somewhere, make sure that you're giving a proper region number. Then concentration also affects your convergence. So accordingly, to a certain extent, only we can go for giving, say, 1e/20, even 1e/21 also will be supported. But depending upon the device we are working with, we have certain limitations with the working principle, working mechanism behind it. Accordingly, we need to manage the concentration as well, doping as well, in simple terms. Then one more thing that we need to consider is step size. Rather than going for a very large step size, it is advisable to go for a minimum step size in order to avoid the convergence. So these are the factors that we consider while we face convergence issue. Okay, so while you start working, definitely at one point you may experience this conversion issue, but that is not a very major problem, which can be easily solvable. But we need to know the techniques of how do we go for solving these kind of conversion issues. Okay, so let me quickly run this particular code. Okay, so this is the, I'm sorry. So this is the structure. So we have the contours, that is doping we have defined, and we can see the junction line, and we can see the electrodes that we have defined, and meshing we can see. So you could see here, this region we have gone for a fine meshing, that is in the junction region. That is we want to go for a very good accurate results is required. So in that case, we are providing for a fine meshing. Whereas here you could see the difference between these two. Fine, this you could see the fine mesh and the coarse mesh. So that's the reason we say it is not every time you go for a fine mesh, since we say fine mesh provides an accuracy. It's not so. Unless or otherwise it is required in the specific region, please go for a coarse mesh throughout your device structure. So that's what we recommend highly. Okay, then now suppose in this case I can see the electric field, and then let me just show you with respect to the net doping, or we can choose the potential. So all these can be viewable over here. And then apart from all these, also if you want to obtain the electron, this is electron concentration. So I can view it as a plot also. Let me just take a cut over here. So yeah, you could see the electron concentration curve over here. So this is not restricted only for these parameters. There are a number of parameters which can be specified in the output statement in the device simulator. For example, if you want to extract the conduction band, valence band, okay, or any other band characteristics. So all these can be defined in the output statement in the device simulator. So this is just one example of how do you update the curve and how do you take the cut line and view it as a plot. Then, yeah, this is the IDVG characteristic. This is by default linear graph. And if I want to view it in log file, yes, select y-axis to be log file. And this is the log curve. And yeah, I'll also try to provide you with the explanation of other things. So annotation. So here in this case, you can adjust your main title. So I can say this is a plot. Okay, so we can adjust our main title. So it is like IDVG. I'm specifying this file, this curve to be. Let me just give some random name. So let me just. Okay, so you could see the main title is being converted to IDVG and the subtitle is curve. Similarly, you can edit the value which you have provided over here or labels name. Okay, and then you can just check your level names. This is the log file name. So if you want to change this log file name, you can change, but I generally don't recommend to do it because this we have written in the code, so it is better to you maintain the same. Okay, one characteristic that I want to let you people know about is like, just imagine the same curve itself I'm considering. So it is in linear curve. If suppose every time if I open, it is in linear. So that is time consuming for me. So what is an easy method to make sure that I view my plot in a log file every time I open it? So in that case, you right click, you convert it, whatever the changes you want to make to the file, you make it and go to file. There is a statement called save set files. So just give that set file, do whatever the work that you want to play with this tool, that is x-axis, title, everything that you want to change, make the change, go here and click save set files. And in the save set files, right now it is the same folder of where I've simulated. So let me just quickly give some name, test.set. And I just save it over here and come to the code where I have written it. In the Tony plot statement, I'm just going to call the set file of what I have created. So I created test.set, but this should be called with the syntax before, it is -set. So let me simulate only this line. Let us see what happens. So you could see it is not opening the linear file. Since I have saved this, whatever the change I have made and saved it as a set file. Whenever I run the set file, this automatically, this data saved in the set file will be open. So every time we need not go right click, change the display, change the log file, or change the like x-axis or y-axis. So if you save it as, you do all the change at one time, you save it as a set file and make sure the set file is available in the same folder of where your log file is available and the input deck file is available. So if it is the case, then automatically when you simulate it, it will open without even going for the previous how you go for the basic default IDVG linear characteristics. Okay, so with this, I will quickly show one more curve characteristic alone, and then we will move on with the mixed mode. So this is with respect to curve characteristics. Yeah, family of curves. So the same code, I'm not taking any other code, I'm taking the same code. So only one definition that will be little varied in this case, that is previously we simulated for only one gate voltage and we simulated the drain voltage and we obtained only one curve characteristic. But right now, if you want to compare the curve characteristic for a different gate voltage, or if you are working for the IDVG characteristic, if you want to work for a different drain voltage, A similar procedure can be followed. That is, I take a gate voltage of 1.1 volt and I save it as a temporary file with an extension of out f is equal to, this is again a user defined name, solve_temp1. It's a user defined name. And then I'm fixing a gate voltage of 2.2 volt, temporary 2, and fixing a gate voltage of 3.3 volt and a temporary 3. It's a temporary file. Now, what I'm going to do is I'm going to load this temporary file. So that is in file. Load in file means you're calling that particular file. So in file, the particular file name. And as usual, you know, before you perform the sweeping, if you want to save the data file, then log file should be defined. So in this case, I have MOS_1. Now I'm loading the second file, that is solve temp2, which is having a data set of gate voltage of 2.2 volt. Now I'm calling this file, ramping the drain voltage. I should give different log file name. If not, it will be overwritten. So make sure you give a different log file name. Third case, I'm loading another file which is having a temporary 3, which is having a gate voltage of 3.3 volt. And this volt, again, it is being called over here, for which the drain is being, drain is being speed from 0 to 3.3 volt. Saved it in a different log file, that is MOS_3. Now, once all these has been done, I'm going to introduce your term called Tony, that is overlay in Tony plot. That is, I want to see all these 3 files in a single window Tony plot. In that case, you use a term called -overlay. So that is, you're going to overlay MOS_1, MOS_2, MOS_3. And I have created a set file because I don't, this is a like IDVD characteristic. By default, you know, this it will be open in IDVG. In order to avoid that, I have created a set file. So when I create the set file, automatically it will be projecting me with the IDVD characteristic of what, or else I can say that settings that I have made with respect to the curve characteristic. So let me just quickly run this. It will not take much time. Just a second. Okay, so you could see here, I have 3 different curves, and this is MOS1. MOS1, red is MOS1, that is for a gate voltage of 1.1 volt. The IDVD characteristic is being displayed. MOS2 is having a gate voltage of 2, that is 2.2 volt, and MOS3 is a fixation of a gate voltage of 3.3 volt. So this is how you update the family of curves using Silvaco device simulator Atlas. Okay. So with this, I will just, likewise, this is all these are DC simulation. Similarly, you can perform AC simulation. So it will take much time, but I can project you with the code. Just a second. One second, I can just open any RF. This is simple hemp devices. So X and Y axis. This is being created using Athena. Structure is then taken forward to the Atlas for further characterization. And then electrode definition, contact definition models will be different for this is hemp device. So you have different model polarization models. You will be having spontaneous and piezoelectric polarization. So everything, all these parameters are with respect to hemp devices. And then you have the method and how many maximum trap, if you're including trap, how many maximum traps should be there. And all others are same. The only thing that I want to show with respect to AC characteristic is, if you're going for finding an AC like AC analysis, you have the log file saved and followed with S dot param, that is scattering parameters all the four, S11, S12, S21, S22, both real and imaginary will be obtained. Then Y dot parameter for admittance and Z dot parameter for impedance gains. It can be intrinsic gain, everything. Like I can say unity gain, cutoff frequency, then you have this power gain. All these gains values also can be extracted in the AC analysis, making sure we provide the input to be gate and output to be drain. Please understand, this is not input, it is input is gate and output is drain. Then we go for frequency sweeping. So in this case, solve, it is going to solve an AC analysis. Frequency with a step of frequency and mult.f is number of times the frequency which we given will be multiplied for 7 times. So that is the meaning. Like we can avoid different steps and give it as in a single line. So that's the reason why we go for mult.f. Similarly, we sweep till 5 power 10. Then we extract the cutoff frequency here. Ft is the cutoff frequency. So we know it is going to be the curve character. From the curve characteristic, we are going to obtain this Ft. So yeah. So it will be Gm by 2 pi CGG. So instead of Gm, you can directly give the differential of the curve. So that gives the that is the your Gm characteristic, and 2 pi CGG. 2 pi is mentioned here as 6.28. Alternatively, you can give it as 2 into 3.14, and which is multiplied with the gate that is capacitance, CGG, gate to gate capacitance. So that's what is given as gate. C is for capacitance, stands for capacitance, and gate to gate. So that's the meaning. So likewise, F max, any parameter that you would like to perform, you can obtain from this AC analysis can be seen here. When you simulate it, you can also obtain the admittance parameters. Everything will be there in the runtime itself. So all the values will be there in the runtime if you specify this in the log state. So unless or otherwise you specify Z dot parameter, it will be computed, but it will not be displayed in the output statement. So if you write it as Z dot parameter, then it will be computed and it will be shown in the runtime output. So this one example that I want to show you with respect to RF analysis. And one more thing, like I think morning we had a question, like if we are working with a user-defined material, so how do we go for all these categories? Means so if we are going for an unknown material that is not available in default in Atlas, in that case, we require a main factor. That is 3 different main factors. That is user group. So first we need to select the material what we are going to incorporate into the device simulator is a semiconductor or an insulator or a conductor. So this should be defined in the user dot group. And then user dot material. This is a material name which the user is going to provide. So I can simply say that my oxide or my nitride, any name, or it is going to be nitride 1, nitride 2. It is going to be a user defined name. So user dot material. So first is user dot group, another is user dot material, and third one is user dot default. That is, by default, we need to call some material that is known material in the Atlas, which is available in the Atlas. Okay, so it could be of any oxide, like oxide family or nitride family, arsenide family. It could be of anything, but a known material from the Atlas library should be defined in the user dot default syntax. So here in this case, you could see my oxynitride is a user defined material, and we could see how it has been defined. I'll give you this particular line. So material statement you can define, region statement you can define. So in region statement, you give it as user dot material is equal to the file name, the material name that we provide. And in the material statement, you give the entire property of what you want to simulate, what you want the Atlas to take into consideration for the device that you have created and for the region you have created. Accordingly, it will simulate. So in this case, you have the material to be your user defined material, followed with the user group, like in this case, just an example of insulator. Default, it belongs to the oxide family. It's just given only permittivity, but apart from that, band gap, lifetime carriers, all the concentration, everything need to be provided in the material statement as well. So this is how you define a user-defined material using this is a syntax. How do you, like an example I can say, how do you define a user-defined material in the device simulator Atlas? Now, these are the materials are available as a default in Atlas. That is single element, you have all these material. Binary, you have these material. Maybe you can, these manuals will tell you how to extract accordingly. You can obtain it and have it as a reference, as a soft copy. And you can see the ternary compound materials, quaternary compound materials, insulators, conductors, organic material that is supported by Silvaco Atlas simulator. So all these material details will be available in the appendix of the Atlas manual. So we can definitely go through it. And without any delay, let me take a minute just to show you how to extract these manuals. So you need not depend on us. So you can go to SMAN. So in SMAN, so we could see, so your window will be open when you open the SMAN. In this, you go to the products section, sorry, document sections. And in document, when you expand it, you go to the product manuals. And in product manuals, you can see Athena, Atlas. So you could see this is user manual in Japanese and this is user manual in English. So you can select and you can give open document. The document will be open. You can save it as a copy in a location which wherever you want. Likewise, this is not applicable only to Athena. You have for Atlas, or I can say basically, yeah. So Atlas I have, and then for Deckbuild you have a manual, Deckbuild you have a manual, Deckbuild 3D. For these are like other tools available in Silvaco. So which you can avoid it. If you're working with TCAD, you can concentrate on Atlas, Athena, Deckbuild, Deckbuild, and then go for Deckbuild 3D, Tonyplot 3D. All these will be available in SMAN. So you can easily extract these manuals and have it for your references. So in this case also, like, so I can just quickly show you the categorization of the models alone. Please give me a quick minute. Okay. Models. Yeah, so here in this case, it is patients. Okay, so these are the models. So under carrier statistics, you have this Fermi Direct, Boltzmann, and then number of models will be included. Maybe I can show the index page alone. Yeah, so you could see like the different models and how to define a structure also, how to define a like 2D structure. If it is a cylindrical structure, how to define in Atlas. All these syntax with an example will be provided in the manual. So you can definitely have a look, and this you could see with respect to equations, what are the equations supported and what are the basic theory that's been supported, different transport model, all these physics models. So everything are available in the manual, so you can have a cross check. So with this, I'll stop the discussion about the device simulator. If you have any doubt, please get it clarified so that we can move on with the mixed mode simulations. So if anyone have any doubt, please get it clarified.
Hello.
So that, yes, please.
Yes, ma'am. I am working in a 3D model. When I put the V drain from 10 to 100 and V step is 10, then it shows the conversion issue, and I didn't get IDVD curve. Ma'am, what is the issue for this?
Okay, so you are sweeping your voltage from 10 to 100 volt.
Yes, ma'am.
Okay,
And
okay.
the step size is 10.
So what you're basically trying to analyze? The simple curve characteristic only.
Yes, ma'am. It's for IDVD curve. It's a TFET structure.
TFET structure. Okay, fine. So, ma'am, first please check with your meshing. Since it is TFET, make sure only in the tunneling region you have a high meshing. Okay, and step size, I think you can even decrease. You told that step size is 10. So please try to reduce that and have a look, and try to increase the iterations, number of iterations. So first point, check with your mesh. So make sure only in the tunneling region it is fine. And apart from that, I'm not saying that it's going to be a very loose mesh in all other part, but still not like of the tunneling region. So first, that
what should be the step size? Like I have put a 10.
Okay, you can reduce it. You can just check how, because I can say with the iterative method only. So you can try with 5 volt and have a check whether it is first solving it, and may know the doping level you're using, ma'am.
Ma'am, 3 e to the power 10. That's
it. Okay.
Ma'am, I have taken ZNO as the active layer, and in that layer I have put the N-type concentration, and the concentration is 3 e to E10.
Okay, that should be definitely supported. So then doping is not an issue. So I think you should check with your mesh, ma'am. Try to reduce your mesh points. Okay. You possibly, like if you are like working for a long time, mesh points will have a greater impact on your convergence. So please try to reduce a little, have a check. And if it is like, for example, I'm just giving an example. If it is solving from 10 volt to 20 volt, and after that, if you're facing convergence, just check if by reducing a mesh to some extent and check whether it is solving from 10 to 20 volt. If it is the case, then you can go for reducing your mesh, but make sure your accuracy and your efficiency depends upon this mesh. So in your tunneling region, definitely you have your fine mesh, but to some extent, not very going for very dense meshing, not required.
Okay.
You can try that, ma'am. Yeah, you can try that. Definitely.
Okay, thank you, ma'am.
Yeah, thank you.
Hello.
Yes.
But
yes,
ma'am,
please.
when we use the fine meshing at the tunnel junctions, we get the sometimes memory allocation failure. Why this occurs? And how to eliminate?
Okay. Is it going very dense meshing, sir? Just a quick check.
Ma'am, any impact of the RAM size of the system?
Okay. RAM, may I know what is the RAM size that you people are currently working with? Because we have recommended like hardware specifications, if I'm not wrong.
Yes, ma'am.
Yeah. So what is the RAM size that you're using?
16.
Yeah, 16 to be appreciated, and that's tunnel fit, right? Yeah.
But sometimes we got the most probably error to memory allocation failure. Can we increase the meshing at the tunnel junctions? And along with the QT mesh.
Okay. So, Engine, you would like to say something?
Yes. So, are you using Windows version?
Yes, sir.
So, Windows version has this issue. Okay. Use this Linux version. So it won't be an issue.
Sir, if we increase the RAM size of the system, can we resolve this issue?
No. Actually, you can see the resource usage in the right-hand side of that Deckbuild. Okay.
Yes, so memory and read write on.
Yes.
Right
so
options.
How much the RAM it's taking it?
I think 1.9 approx 900.
Okay. So let's say let it be 1 GB, but you are having 16 GB now. So it's because of that Windows support compatibility issue. Okay. So to get 100% compatibility, you can go for this CentOS and RHL versions. Okay. So other than that, it won't work. The Windows versions, the compatibility version, compatibility issue is there. Okay.
Sir, my next question is to how to get the netlist when we design and simulate any device for the circuit application. How to extract the netlist from this by using Silvaco?
let's say you are creating a device and you want to take it to circuit simulation, is it?
Yes, sir.
So which for a different tool?
It's a third-party tool or what? Just to
is it
know.
a same Silvaco?
Yes, sir.
So third-party tool. So we cannot do that. Okay.
So in third-party tool, what you need to do is like the TCAD result. First, it need to be modeled. For modeling, we have a separate tool because this is only about TCAD. And from the compact model, what you have extracted, the spice parameters, you can take forward to any third-party circuit simulator tool. But if it is a simple structure, I think like simple analysis, I think you can go ahead with mixed mode simulation as well. That's what we are going to see. Engine, you can just carry forward.
Yes.
Okay. So one more question alone is there. Let me answer that, and then I think we can start with the mixed mode. And Mr. Prabhat, like, do you have any other questions apart from this?
Okay.
Because if you want to take to a third-party tool, then obviously you have this TCAD results need to be performed with a compact modeling simulation. It is supported with various compact modeling models, and from which you extract the spice parameters and fed into a circuit simulator. This is the actual scenario. Directly, you can't take it plugin, definitely.
जो एक्स्ट्रा टूल है उसको उसका नाम क्या
है? We have the Atmosphere for compact modeling, and then we have Smart Spice for circuit simulations.
तो क्या ये जो हमें सिल्वैको का लाइसेंस एक्वायर करते हैं कॉलेज कैंपस में, तो इसके साथ ये हमें यूज करने का ऑप्शन नहीं होता?
That is actually comes under different purchase. So right now it's about TCAD. So under TCAD we have showed what are all the possibilities. We are focusing towards the device simulations.
Okay.
TCAD is meant only for performing device simulation, mimicking the fabrication steps and characterizing what we perform. So apart from the circuit simulation, we need a different tool.
Okay, ma'am, if possible, little bit can you explain in this session?
About the circuit, I mean the compact modelings, all such?
Extract to the netlist of any device simulated on the TCAD.
Okay. Simulated on TCAD. TCAD you can't do it, sir. That's what we are saying. So right now, Engine will be explaining with the mixed mode simulation, that is combining the device and circuit simulation for a simple structures, simple circuit.
Okay.
So that will be done, and he will also explain you with all the netlist extraction, everything. But we are going for a complex one. Then in that case, you definitely go for a, like for example, I can say you go for a Verilog game modeling. Am I right? So that's how you fed into a circuit simulator. So those kind of complex models, you need a separate tool. That doesn't come under TCAD.
Okay. Thank you, ma'am.
Yeah. Okay. Thank you. So I will quickly answer to Mamata's question. So it is about like, can we change some material parameter values and how we can do that? Definitely, you can change the material parameter values. Under the material statement, you need to call the syntax of the parameter that you want to change. For example, I'm just giving a rough example only. So if you want to change the value of the band gap, so you call this, it is available in the manual. You can definitely have a cross check. So you include that syntax and you change the values. Yes, please.
Ma'am, your screen is not visible if you are showing.
Pardon? I couldn't get you.
Ma'am, are you explaining with the slide?
No. I'm just answering her question. That's it.
Okay. Thank you.
Yeah. So that is what with respect to that is material, specifying the different values for the material parameters. So any other question? I think someone have raised the hand. I think either they can. Yeah. Yes, please.
Ma'am, you have shown that how to overlay cars, cars from same devices. Can you overlay from different devices?
Yes, sir. Definitely. If it is under the statement of dot lock, you can. What you can do is just let me just quickly project the screen 1 second. So right now I have overlaid. I've written the overlay statement directly in the Deckbuild platform. Am I right? Well, alternatively, if you want to open 2 or 3, for example, I have a IV characteristic of one device which need to be compared with an IDVG characteristic of another device. In that case, directly I go to the Tony plot, open that particular file. So I'm just giving it as a random. So this is one file. So I have it in IDBD. Okay, I'll just select IDBG. So I'll have more example for it. Yeah, this is IDBG. Okay. So this is what you're asking. So let me open this. So this is IDVD, I guess. So let me try to overlay this with the other simulation that I have performed. I mean, other code I have performed. So to do that, I go to the like this open document. We need to go to the locator of the file which is presenting. So in this case, it is this file. Okay, you need to go to that. And here in this case, you select overlay plot. So add plot means next to next the window will be open. Like morning engine was showing one particular structure file comparing with another next to next, right? But in this case, I can overlay the log over here like this. So you could see. So I have taken, this is from another code and this is from another code, but I have overlaid both the curves.
Okay. And madam, if another question is that if we want to do the log and linear in the same graph, can we do it in the log and linear in the same graph?
What you can do is you can include the mixed y-axis, y scale. So y2 scale, you make it as log, and y1 scale. In this case, I haven't given the data. So in this case, y2 quantities you can select. Let it be the same drain current. Okay. And so let me select. So you could see both the side the curve has been created. Linear has also been created. Log has also been created. So y1 is linear and y2 is the log. Okay. So likewise, you can select both linear and log in one window.
And I was thinking that you are ramping from 0 actually in gate voltage. And
okay.
Can we ramp from -1? That is, if you show the negative side of the.
Yes, yes, you can ramp from -1 also.
So won't there be any error? Actually, they are giving error actually if I'm ramping from -1.
Oh, is it so? So let me just quickly check, but it doesn't. I don't know what is the file name. If not, I can quickly open and show you. I already have for the ramping of negative voltage. Just a second. I think it must be somewhere here. See what is the voltage being given here. This example. Yeah, in this example, this is hemmed. So where I have spec from gate voltage, fixing the drain voltage to be 1 volt. Gate voltage, I'll run only the DC characteristic.
Yes.
I think that should be fine because it will take some time for the AC simulations. So here in this case, we have fixed the drain voltage to be 1 volt and the gate voltage, it is -8 volt. Okay. So it will be ramping till -8 volt. And then we are again saving the log file till 1 volt. So we'll see how it is taking into consideration. Just a quick minute. So this is hemmed, so it is taking all the polarization, spontaneous. So the module is blaze because we use different materials, yeah, compound materials. Okay, let it simulate. So we can move forward with the next topic. And once the simulation is done, I will share it. I'll share the results. Yes. Thank you. So engine, I think you can start with mixed mode. So by the end, I will just project them with the results.
Okay. Okay, sure.
Yeah. Thank you.
Please make me a host.
Sorry, one second. Already I've made you. Okay. Yeah, fine. I've made you. Please go ahead.
Yeah, sure. Is it my screen is visible?
Yes, yes.
Okay.
So it's like it started screen sharing. Yeah, it is visible now. Yeah.
Yes, yes, sure.
And Angel, if you don't mind, like, since you had this page, can you just quickly show them how to view the applications in website just for a minute, and then you can
Yes,
start.
yes, sure.
Thank you.
So actually, I took this page for this user-defined material. So first, I'll tell you that. So like it's like user-defined GA203 is not available in Silvaco, so we define as user.material and GA203, and followed by that in material file parameter we call it this, and user default will be GAN, and user group will be semiconductor, and affinity. So all those other parameters like permittivity, band gap, okay, and hole mobility, okay, conduction band density. So like this, you can define your user-defined materials, okay, and then you can do the simulation, okay. So I hope you understand about that. Now let me go to the Silvaco example itself, okay. So in morning session we seen about examples in tool itself. Okay, so if you go to this silvaco.com and example slash index.html, so you will get the examples updated. So every month they will do an update. Okay. So let me just go to TCAD examples. Okay, so you will be seeing this as usual, the same examples will be there, plus additional examples also will be there. Okay. So let's say morning we seen about this MOS application examples. So there it will be around 15. So here it's additionally 3 examples additional they have given. Okay. So they will update every month. Okay. So as usual, same thing. What you have seen in the tool, the same thing will be displayed here. Okay, the complete details about this example, and you can check the input deck code also. If you click here, and you can check the deck code also. Okay, and the structure and the output also will be displayed here. Okay, so that you can easily check from the TCAD examples. Okay, so I think let me move to the next step. Okay. Okay, so we'll start with the session for the mixed mode circuit simulation. Okay, so what is mixed mode is? Mixed mode means two. Okay, so mixing two different differently oriented device. Like first one is a device, okay, your physical device and your circuit. Okay, these two you are going to combine together, and you are going to check how these two will perform together. Okay, which in our case, which is a device which is created in Atlas or Athena or whatever may be. And once the device, like let's say you take a MOSFET, you create a device in Atlas device simulator, and you want to incorporate with some circuit, like you want to do some amplifier or oscillator. Okay, so for that you need some circuit elements like resistors, capacitors, inductors. Okay, so these things are inbuilt available in Silvaco, so that you can make use of it, and you can do the circuit simulation like amplifier and for oscillator and so on. Okay, for your need. So moving to the introduction part. Okay, as we spoken, the mixed mode module. Okay, it's a module of an Atlas, which is device simulator itself. Okay, and it uses circuit simulation and along with it physical based models. And its features is its ability to link any mesh device. So mesh device means the device will be created using Athena or Atlas 3D or Deckbuild or Deckbuild 3D. So whatever the device, in whatever the format it's created, we can take the device and do the circuit simulation. Okay, and you can do multiple mesh devices. Like let's say you are having let's say you are taking one CMOS inverter. Okay, so which contains one PMOS and one NMOS, right? So you can create a PMOS separately and create an NMOS separately, and you can along with it link it together and do the circuit simulation. Okay, so multiple devices, like up to so in default it will support up to 10 multiple devices it will support, and with the independent models and material parameters. Okay, so in this mixed mode we can do DC, transient and small signal AC analysis in this. And mixed mode circuit can include up to 200 nodes, 300 elements, and 10 mesh devices. So 200 nodes is like circuit which contains different connections and combinations. This is what called nodes. And 300 elements we have seen, right? So what these elements is the circuit elements which is present there, like resistors, capacitors, and all those things. And the 10 mesh devices means the device what you create. Okay. So followed by that, the circuit elements supported in the mixer modes are, okay. You can see these are the different circuit elements which is supported. You want the voltage sources, okay. You can make use of it, like voltage control voltage sources, current control current sources, voltage control current sources, okay, current control voltage sources, okay, and let's say resistor, capacitor, diode, okay, coupled inductors, okay, inductors. And so you, for example, you create one N MOSFET and you want you don't have the P MOSFET to include with it, okay, for a CMOS inverter. You can call this MOSFET device also. So this MOSFET, NMOS, PMOS, so which is already defined here, and MOSFET, and optical sources for solar cell based simulations, okay. And you can do like optical sources means light source for the solar cell, and the BJT devices. So all those things we can include, which is present in circuit element that supports in mixer mode. Okay, so the approaches of the circuit performance to be analyzed. Okay, so these are the two approaches. Okay, like you create the structure from Athena, which is process structure. Okay, and you can perform with Atlas simulation. We have seen the, in previous sessions, and you can get the parameter abstraction. Okay, and after that, from Athena to Atlas to circuit simulation, you can perform. Or else, like there is a second another easy method to the circuit simulation, which is called mixer mode simulation. Okay, so we can directly call any structure into mixed mode simulation and perform the circuit simulation. So mixed mode is kind of easy mode to do the physical device and circuit simulation. Okay, so we'll directly go to the example. Okay, so basically I'm going to perform the circuit, which is NMOS non-inverter. Okay, so which contains two inverters connected together. Okay, so this is an one inverter, this is a second inverter. Okay, and this is a NMOS, and one device I'm going to create, and another device I'm going to call it from circuit element. So resistors, capacitors, voltage sources, so everything I'm going to call it from circuit element. So this I'm going to show you how I'm going to do. Okay, so this TCAD device, which is NMOS, this is the structure I have made it. Okay, basic thing, like it's a silicon. Okay, the channel will be silicon. So NPN channels will be formed, and in I just applied some source drain contacts and gate contacts. Okay, to just to perform just an NMOS structure. Okay, to get the basic idea about this, and I'm going to call it in a mixed mode and perform this circuit simulation. So let me directly go to this. Okay. Okay, so let me just show you. So initially you need to create the structure, which is NMOS in our case. Okay, for that, go Atlas, mesh, out file, nmosfet.str. Okay, and master.out, which represent, it will give all the permission to the structure. okay, which is created. And as usual, same thing, X mesh and Y mesh, okay, to create initial case we do, and creating the regions, okay. The channel will be silicon, and the oxide in the gate oxide will be oxide, okay. Then we'll apply, we will create electrodes, okay. So the electrodes will be like a gate, source, and drain. Its coordinates I have given, okay, and followed by the doping profile, okay, N type, P type. I use this Gaussian and uniform type profiles for it. So let me quickly show you the structure, how it looks. Okay, so this is the structure and basic silicon channel. And so above that, a thin layer of oxide. And above that, you can, if you just zoom and see, so there is a thin line. Okay, I hope you cannot able to see. Let me just show you the contacts. Okay, so you can see it was highlighted in some blue color. Okay, which is source and gate and drain. Okay, let me just zoom it even more. So if I remove this color, I think you can. Okay, so you can see here. So this is the. So let me just remove these lines also. Okay, so now you can able to visualize the source, gate, and electrode and substrate contacts also. So this is the basic structure which is made it. Okay, and let me show you the doping profiles, which is N, P, and N. Okay, and in center it was a channel, and so just made a basic meshing to simulate this structure. Okay, and followed by that, now we'll go for the circuit simulation part. And so here we write, we create a netlist. Okay, so the netlist, which is an universal netlist. So what we can use in like different tools like this Smart Spice or some different tools. So whatever the netlist we use, the same netlist syntax it will be. There will be no changes. So it will be starts with Go Atlas, because mixer mode is an Atlas on module. And to start the netlist, it should be starts with .begin. Okay. And initially I have made one code which is called DC point simulation. So what is this DC point simulation is? So DC point simulation, so it will initialize the initial guess of the circuit and the structure, okay, Atlas structure, okay, and then we'll perform the DC characteristics and transient response characteristics, okay. So this is the netlist, okay. So how to write this netlist is very simple, okay. So let me go to the this diagram, okay. So while drawing this diagram, okay, you need to visualize yourself, okay, and you should name it each nodes, okay. Like let's say this MOSFET's source is connected to 0, okay, and this power supplies negative is connected to 0, okay, and VCC power supply is connected to 0, and this MOSFET source is connected to 0, okay. The capacitor negative is connected to 0. So 0 is an imaginary name you should be thinking, okay. You should visualize yourself when you are creating it. So let's say 0, 1, 2, okay, and 3 and 4 all are like visualizing numbers that you need to visualize yourself when you create a structure, okay, while you're drawing the circuit, okay. And so now let's say so these numbers are called nodes, Okay, so we have seen up to 200 nodes it's supported. Okay, so up to 200 nodes it will support in mixed mode. Okay, so now we'll connect each and every components with this node connections. Okay, for that, the first thing is you need to know about this circuit elements and its special syntax. Okay, so let's say this is an Atlas device. The first one is Atlas device. In bracket, I have defined as A device. Okay, let's say it's an voltage source. Okay, independent voltage source. It will be V device. Okay, so what is this single letter thing? Okay, so that we'll see what is that. Okay, let me go to the code. So initially I'm going to include voltage in. Okay, so in the circuit Vin, this is what the Vn is. Okay, I'm going to create this. Okay, so since it's an independent voltage source, okay, so the independent voltage source, the syntax is V. Okay, the first letter in mixed mode, the first letter defines everything. Okay, so after that, whatever things you can return, that's not a matters. The first letter defines what the device will be going, what is that device. Okay, how it's going to work. Okay, so here for independent voltage source V. Okay, so V is an important syntax word for an independent voltage source, and followed by that user defined name. Any name you can give, like 1 2 3 you can give, in or out you can give any name. Okay, you can give. So I'm giving it in. Okay, so followed by that syntax will be plus node and minus node and the value, initial value. Okay, let me tell you again. So V represents, okay, it's a syntax for an independent voltage source, and in represents your user defined name. Okay, it can be any name you can give. Okay, without space. Okay, without any special characters, you can give anything. Okay, and followed by that plus node and minus node and the initial value. Okay, so now we'll see the circuits. Plus node is where it's connected. Okay, the plus node is connected to 1. Okay, the minus node is connected to 0, right? So that is what it defines. The plus node is 1, minus node is 0. The initial value of the independent voltage source is 0. So why I'm giving 0 is I'm going to ramp this voltage source. Okay, so I'm giving it as an input. Okay, so initially it will be 0. So later I will going to ramp it up. Okay, to perform this characteristics. Okay, so the next one is your Atlas device. Okay, to include this Atlas device, the first letter defines A. A should be there. Okay, if your device you are creating it in Athena or Atlas or Deckbuild, so whatever it should be, the first letter should be A, followed by that any name you can give. Okay, it's a user defined name I'm giving. Since it's an NMOS, I'm giving it as N. Okay, followed by that each electrode should be connected to which nodes. Okay, let's say drain is connected to 2. Okay, gate is connected to 1 node. Okay, source is connected to 0 and substrate is connected to 0 since it's an NMOS. Okay, so let me show you that. This is the device. Source is connected to 0. Okay, gate is connected to 1 and drain is connected to 2 node. Okay, so that's what it's defined, and substrate is connected to 0 since it's an NMOS. Okay, so now we have defined the nodes. So now you should declare so what structure it should take. So for that, in file, and so we created this structure in the top. You can see here nmosfet.str. The same name you should be given here. Okay, nmosfet.str. Okay, and width you should be providing it. Okay, so by default the width will be taken as 1 microns, and if you want to change it as per your requirement, you should be changed. So width equal to 15 microns, I'm setting it. Okay, so here the voltage source is done. Okay, and this Atlas device is done. So now we'll include this library element MOSFET. Okay, So here the MOSFET, which is called M device. Okay, the M is a syntax. So the same thing M, okay, and followed by that user-defined name, and followed by that syntax will be the node of drain, gate, source, and substrate. Okay, so let me tell you again. M is a syntax for MOSFET, and N is a user-defined name, any name you can give, and drain, and gate, and source, and substrate. Okay, so which node it should be connected? 3200, right? So let me go to the thing code. So 3 is connected to source, 2 is connected to gate, 0 is connected to source. Okay, so 3 is connected to drain, and substrate will be connected to again 0. Okay, so this is what it defines. So now what is this simple? Simple is a user defined model. Okay, any name you can give here. Okay, so any name, like demo, you can give any name. Okay, you can give it here. So why we are giving any name? So how we are going to call it in background, that we'll see. Okay, so here now we need to define its parameters. Okay, so what is this MOSFET, right? So in this MOSFET, so what the basic parameters will be channel length and the width. Okay, so the channel length is 2 microns and width is 5 microns. Okay, so not only 2 parameters. Okay, there are different parameters are available. Okay, so that you can check in manual. Let me show you. So if you search about the mixer mode,
Then just please give me a minute.
yeah, sure.
So Dr. Gopal, so can we take another 10 to 15 minutes? Will that be fine?
Is it for break?
No, not for break, because I think you require 10 to 15 minutes, right?
Okay.
That's what I'm just taking his permission, because we are supposed
to.
Sure. So Dr. Gopal, you're there? Like, can we take another 10 to 15 minutes? Will that be fine?
Hello?
Yes.
Okay. Thank you, sir. Thank you for the time. So let me just start with this, which is MOSFET. The syntax is as usual the same thing. Okay, so M defines MOSFET element. Okay, and XXX defines any name you can give. Okay, which is customer user defined name. So ND, which is defines node drain, node gate, node source, and if anything node substrate or node base is there, you can give. Okay, so M name is a model name, so that we'll define. So initially we have given L and W, which is channel length, okay, and a channel width. Okay, these two things we can give, and additional parameters also we can give. So AD is a drain diffusion, source diffusion. Okay, and so likewise you can give initial state. Your device would be on or off. Okay, your IDVCS values. Okay, so your device temperature. Okay, so everything you can change. So in our case, I haven't defined all those things. So if I don't define this, it will take as a default values. Okay, so let's say AD, the drain diffusion junction will be 0. Okay, and likewise it will take default values. Only this L and W will not take default values. It should recommend to give. Okay, so if you check in manuals, you will find all the parameter syntax and its description. Okay, so now let me move through it. So now we have defined voltage source, okay, which is a Atlas device, how to include it, and MOS device, and followed by the resistor R1 and R2. Okay, it's the same thing. R represents the circuit element name, followed by the user defined name, plus node, minus node, and the value. Okay, so let me tell you again. R defines the resistor circuit element, it's must, followed by the user defined name, and followed by that plus node, minus node, and the value. Okay. So it's connected to 2, 4 and 3, 4. So let me check. Okay, it's connected to 2, 4 and 3, 4. Okay. So since resistor is any bidirectional, you can connect bidirectional and you can change the node value. There's no issues in it. And followed by that VCC. So VCC, I'm applying 4 volt. Okay, so which is voltage source is V, and CCC is a user-defined name, plus node and minus node, and the value of it. So VCC 5 volt will be applied in the 4. Okay, so let me show you. So VCC, the plus node is connected to 4, the minus node is connected to 0. The 5 volt will be applied for a power supply for this circuit. Okay, as usual goes for the capacitor. The capacitor C1 defines as 3 femtofarad, and it's connected to plus node is 3, minus node is 0, and the value is 3 femtofarad. So that's what it's written. C, okay, 3 plus node, minus node, and the value. Okay. So this is what the netlist is. It's very basic and very simple. Okay. You can do this type of writing netlist is very easy. And followed by that, so I told you simple. What is the simple is? Okay, simple is a user defined any name you can give. So why we are giving it is, so we have defined this as a MOSFET. So we haven't defined it's a P type or N type, right? So that we are going to define. Okay. So for that dot model, simple, the same name you should define. Whatever the name you given, you should give it here. And followed by that, it should be NMOS. Okay. So here I choose it as an NMOS. And if you want to choose PMOS, you can try here as a PMOS. Okay. So the basic characteristics need to be applied, which is threshold voltage will be 0.02 e power minus 6. And the threshold voltage of this device will be 0.9. Okay. 9 volt. And followed by that dot numeric volt V change defines voltage change, okay, as 1. Okay, so what is this voltage changes? So in the circuit it contains up to 5 nodes. Okay, 0, 2, 1, 2, 3, 4, 5 nodes. So in this each node at the time of simulation, the voltage change will be like 1. Okay, like if let's say input voltage is applied 0 and then 1 and 2. Okay, so the each node, the variations in different due to this gate will be 1. Okay, only one changes will be occurred. One step value will be done. So it's kind of step value. Okay, in each node, and followed by that dot options print. So M2LN is called Newton method. It's a modified 2-dimensional Newton method. And the no shift is like, so it's a special syntax. Why we are defining is in circuit simulation, sometimes the solution will go for on convergence. Okay, the solution will get converged. So sometimes in Newton method, what they will do is, let's say the gate voltage is 5 volt and it cannot able to find the solution. It will take lesser value as 5 volt, 2.5 volt. Okay, so those type of issues, no, that it will ignore. It will simply ignore. For that we are declaring it as no shift. Okay, and I'm just saving it as save dot out file equal to nmos. It will save it as nmos.car, which is circuit file. Okay, so the initial guess will be saved in this file. Okay, so dot end followed by the dot end. So we are just defining it a contact work function. Okay, so if you have a own work function, you can give. Okay, or else like you can leave it as it is if you choose a different material. Okay, so in my case, I choose just a conductor in a structure. So I am choosing the gate electrode as polysilicon. Okay, so followed by that you should apply some models. So models device name is AN. So this AN, you all know, this is you have what the Atlas device line, the same should be called B over here. And region number 1, which is silicon, the channel region, I want to apply these models. Okay. So I'm giving this mobility model and band gap Nora model for the basic MOS simulation. Okay. And followed by that, now I'm going to do the DC curve simulation. Okay. So, so this node sets, right? The net list, which is same. Okay. So the same net list, I just copy pasted here. Followed by that, so previously I used modified two-dimensional Newton method. So here I'm going to use full plused Newton method. Okay, for that the method will be full N. Okay, and the same thing, no shift. Okay, so the initial value, initial guess, I'm calling it here like dot load in file and MOS. Okay, so initial guess it will be called inside this loop, and I'm just saving it as in log out file and MOS DC. Okay, and here the additional parameter is dot DC and VIN. Okay, the VIN is what you have provided here. The same name should be there. Okay, so VIN, and the syntax is, so it should be connected so V in and initial voltage at the final voltage and the step voltage. Okay, 0 is the initial voltage, final voltage is 5 volts, and the step voltage is 0 to 5. It will go like 0.25 and 0.5, 0.75 and 1 volt, like that it will step. Okay, and followed by that same thing, everything is same. Okay, so I just simulated already since it takes some time. Okay, so let me just plot this log plot. Okay, so initially it will shows like this. Okay, so now I want to show you how to choose in Tony plot. Okay, so basically we see output characteristics like in the graph. Okay, how your device performs is input versus output. Okay, so V1 is an input. Okay, so let me go to the structure again. So this node is an input, right? The node 2 is the first inverter output, and node 3 is a second inverter output. Okay, so let me just show you that. So I'll take x-axis as V1. Okay, and y-axis also I'm taking it as V1, and you can see it is ramped up. Okay, so 0 to 5 volt at the step voltage of 0.25, it will ramp up. Okay, so due to this, let me go to the circuit. Okay, so let's say initially it's 0 volt. Okay, the device will be at off state. Okay, and 0.5, and until it reaches the threshold voltage, the device will be at off state. Okay, and the output it will come as like the direct VCC will be applied directly to second node. Okay, so which is 5 volt we'll get. Okay, when the device is at off state. Okay, since it once it reaches the threshold voltage like 0.9 volt or 1 volt, okay, it started to conduct. Okay, so then this it's connected to negative, the electron started to flow from here. Okay, so the electron will started to flow to downside. Okay, so then it will reach to 0. Okay, so this is the function of this circuit in the first inverter. So basically what it is if you give 1 as an input, so you will get 0. So V1 is the input and V2 is an output. Okay, so this is the first inverter output. Okay, so you can clearly see. Okay, so at the initial case, the transistor is at off state. So since it's in off state, there is no electron flow. Okay, the VCC directly applies here. Okay, you are getting 5 volts. Once it's the device reaches the threshold voltage, you can see there is a sudden drop. The electron started to conduct from source to drain. So the graph will start drops to 0. Okay, So basically you are giving a 1 as an input and you are getting at 0 as an output. So now this V2 is an input and V3 is an output for the second inverter. Okay. Same thing goes for that. So V2 and V3, I'm just comparing it. Okay. So you can see here. So once it's in higher voltage, high, for the second inverter, okay, so it's at off state. So once it's come to 0, it started to conduct. Now VCC directly applies. Okay, I hope you understand this graph. Okay, you understand. If you have any doubts, you just ask me. Okay. Okay, I hope you understand about this. So let me just go to the next part is you can directly check your drain biasing. Okay. So how your device performs. This is an IDVG curve of your device. Okay, your MOS device. And each nodes you can select differently and you can verify it. Okay. So now the DC simulation is done. So now we'll go for the transient response. Okay. Okay, this is a transient simulation. So to do the transient simulation, everything is same. Okay. So in we are giving a pulse. Okay. One pulse we are providing it. So which is like initial voltage and higher voltage, delay, rise time, fall time. Okay. And the period, which is the width of pulse, which is 1000 picoseconds, and the period of the pulse, which is 10 seconds. Okay. So this you can define in different ways. Like, so if you are doing it in amplifier, you can use sinusoidal, cosine, exponential. Okay. Like different input pulses you can provide. So which is available in the Atlas manual itself. Okay. So let me just show you. Okay, so this is the transient parameter. So which is exponential waveform you can give. Okay. And Gaussian waveform you can give. Okay. And pulse waveform you can give. The pulse is what we have provided now. Okay, its complete details will be shown here. And you can provide this piecewise linear waveform. And okay, and SSFM, which is sinusoidal waveform you can give. Okay, and sine waveform you can give. So likewise, you can do different waveforms as an input. Okay. And everything goes the same. Okay. So before we use this dot DC, here we are going to sweep the time. Okay. So for that, the sweeping is transient time, which is around 0 seconds, which is 0.001 picoseconds initially, and ends at 3 nanoseconds. So from 0 to 3 nanosecond, how your device works. Okay. So everything is same. So let me plot the transient response. Okay. So initially something curve which shows it is capacitance. So you can always remove it. And the x-axis is transient time. Okay. So 1 is an input source we have provided as a pulse. Okay. Okay, so this is the pulse we have provided. Okay, so initially it's 0 and 5 volt and rise time and fall time. Okay, the pulse width is 1000 picoseconds and the complete pulses period, which is 10 seconds. Okay, so that you can provide. So now, so we'll see the input is 1. What is the output of the first inverter? Okay. So you can see when the pulse is high, the inverter was inverted to inverted. Okay, so you're getting the inverted graphs. Okay, so when it's high, the output is 0. So when it's low, the output changes to 1. Okay, so now let me hide this input. So now V2 is an input for the second inverter, and let's go with the third one. Okay, so as usual, same thing. Okay, when input is 0, okay, the output is 1, and when the input is high, the output is 0. Okay, so if you have any doubts in this, do ask me now. Okay. So
Hello.
I hope, yes.
Sir, if we use some other device like FinFET or TFET in place of MOSFET, what should I represent for in place of M?
So for actually the first step when working with the mixer mode, first you develop your structure in Atlas itself. Okay. So let's say your like FinFET you are working. Okay.
Yes,
so in FinFET, the Atlas simulation itself, you get the characteristics. Okay. So IDVG, IDVD, whatever the parameter you want, you can get the characteristics. So then you will get the idea about what model should be used. Okay. And what method should be used and everything. Okay.
Yes.
So and everything is same. Okay. Just you need to call the structure here. Okay.
Yes, sir.
And FinFET, since it's in 3D, you no need to give the width. Okay. And
so
followed by that. Yes.
If in simulate in 2D, like for example, TFET device.
Yes, TFET.
So we need to define width.
Yes, you should be defining it.
But if a width may vary, some points extend like 10 nanometers for 0 to 10x nanometer to, and for further 10 to 15 nanometers, so it should be 5 nanometers. Then how can we define with this?
So with this, it's in microns. Okay.
Yes.
So let's say you need to be in 100 nanometers. Okay. So you can give 0.1 microns, which is 100 nanometer. Okay. Or you can give it 10 nanometer, like 0.01.
Okay.
So it's simple thing. Okay. So every value is in microns. You need to convert that. That's it.
Sir, just the last second one line MN3200 simple L. If the length of the device may vary near the drain side and near the source side, different length for the channel length.
Yes.
So how we can define?
At the time, you cannot go for this. You need to create the structure in Atlas, and you can include it here.
Okay, the same process as the previous one. AN.
Yes, same thing. So AN, so which is followed by user defined name, and you can just call those nodes and the input structure file and width. That's it.
Okay. Thank you, sir.
Okay.
Excuse me, sir. If we want to give parametric variations, how we can give that? And we want to study the process variation effect.
Process variation means I don't understand.
Process variation, I want to study random dopant fluctuation effect. Suppose I have defined it, my channel length is suppose 10 micrometer, and due to process variation, there is some 3 sigma variation. So generally we are using this Monte Carlo simulation technique.
Yes.
So how to incorporate that Monte Carlo simulation, how to use that Monte Carlo simulation here to study this process variation impact?
In the circuit simulation, is it?
In circuit simulation or in the device simulation?
So, okay. So there is a bunch of examples. So in Atlas itself, you can do all those simulations. Okay. If you check in examples, you can find that.
Monte Carlo simulation we can perform in the process simulator Athena. So which type, may I know the material that you are working with now?
Basically, right now we are working on MOS2, but that is not available with this software, no?
Yes.
Okay, so previously we have worked on the simple silicon, and we want to see this PVT. We are doing PVT analysis. Okay, and then we have done this Monte Carlo using Tanner.
Okay. Yeah. So Monte Carlo models for the fabrication, that is process simulation step, it is available, but it is limited to few materials with respect to Athena. So that's the reason I just initially checked with you what kind of material you're working with. Maybe 1 second, you just give me a quick second. Let me try to open it in my laptop. So what are the material that has been supported for Monte Carlo models in Athena? Please just give me a quick second.
Oh.
Yeah, so I think morning I've showed an example with respect to silicon carbide, if I'm not wrong. So silicon carbide is supported. Yes, silicon is also supported. A few other materials are also being supported, but not all for Monte Carlo.
Okay. Can you give us one example that how to use that Monte Carlo simulation?
Let me just quickly check if there is an existing example available. I can project this. Yes. Just a quick minute. Okay, so here is an example. 1 second, let me project my screen. Okay, so one example is available, but this is with respect to silicon carbide. So where you have this MC implant, and let me load the code and just give you some rough idea about it. So you have this BCA. So for Monte Carlo implantation, we follow this BCA method. So let me just open the manual as well. So yeah, so implantation model. So we use the Monte Carlo BCA implant model, and it takes account both the crystalline structure and compound materials. So we have these material that is supported, silicon carbide, and then silicon and few other. I'm actually, it would be mentioned, but I'm just quickly checking. I don't remember the page number, that's the problem. This, maybe you can go through this example, but this is for silicon carbide. You can have a look. To etching. Okay, so I'll just tell this example name. Maybe you can have a note and have a look. It is silicon carbide EX04. So this is carrying out with the MC implantation, Monte Carlo implantation, where BCA model is being used. And any other example. So here another one. It is also like 2D BCA low energy boron and drain implant. So in this case also, let me load. We have this BCA implantation, that is Monte Carlo. Then this is not there. So here in this requirements itself, we can see MC implant is being used in this particular model or not. Yeah, here in this case it is used. And for this one also you can use. I think there are a number of examples. Maybe you can have a cross check, and these are not limited. This involves other material also. So specific silicon carbide, it will be under the category of silicon, section of silicon carbide. If not for other materials, it just like you can just refer to the load and refer to the example of what material is being used.
Okay, so we can give the parametric variation to all the structure dimension as well as to dopant fluctuation and all that stuff.
Definitely we can if I'm not wrong, you're expecting like some kind of optimization or
yes,
design of experiments, like varying one parameter or all other parameters.
Yes, simultaneously. Either sometimes we have to give one variation and keeping all other.
Correct.
So
exactly. Sensitivity analysis.
Yes. Okay.
So definitely you can perform, ma'am. But in that case, you need to use a loop statement, like loop statement. Hope you have heard, like how we have in C language. Exactly similar kind. You can use a loop because we have a dedicated tool specifically to perform design of experiment optimization. So, but in TCAD, if you still want to perform those kind of oscillation, like just take an example of where you're wearing a gate length. So you want to vary from 40 nanometer, 50 nanometer, 60 nanometer. So in those cases, you can put it in a loop. The gate length can be called in a loop. So accordingly, the device will be taking the gate length and provide the simulation, and it will overlay the plots as well.
Okay.
You can have an easy comparison. So it is possible.
Okay. So in future also, if we face any problem, then we will definitely look forward.
Yes, definitely, undoubtedly. You can check with us, and without any delay, I think I have taken more time, so I'll just quickly show. You're asking for the negative simulation, the negative voltage. So I think I've simulated one. So this is the code where we have simulated with respect to the negative voltage. So this graph is also for the same. So it has been simulated from -8 to 1 volt. So I would like to show this. Yeah, negative voltage can also be simulated using the device simulator Atlas. And one more thing, in Silvaco website, if you just go to the support, I think engine have shown like application examples. There are number of application examples available. So since we are working with TCAD, these are other tools that are available in Silvaco for various work to be carried out. That's what I told. If we want to perform any compact modeling simulation, then we need to go for Atmos 4, which connects the TCAD to a circuit simulator. It acts as an intermediate tool in order to link the TCAD with a circuit simulator, any circuit simulator it could be. So in our case, we have the analog simulation to be carried out using SmartSpice and other tools like Gateway, Guardian, and Expert. So right now in TCAD, we have this process and device simulator. So let me just quickly move on with that. And number of examples with respect to BJT, or it could be diode, or it could be ferro. You're working with a GaN-based, like completely GaN-based HEMT, or other material HEMT devices, or you are working with a high-K dielectric material, you're working with laser, LED, everything, or if you're working with optoelectronics, organic material. So you need a general basic idea of where should I start with. So in that case, you can definitely refer to all these example. Various parameters have been extracted, and the results of the same and the deck code of the same are also available. Both in Silvaco website, as well as you can embed from the Deckbuild directly itself. So this is support. And one more thing, I would like to share the mail ID with all of you. So if in case if you have any problem while you're working and you want some clarification that need to be provided, so in that case, definitely you can reach out at info@cognitivtech.co.in. So one of our team member will be readily available in order to extend the support with respect to your query. So it is info@cognitivtech.co.in. So if you have any questions, I think we are ready to answer your questions.
Ma'am, at most and smart spice is free for the student. Some license.
It is not free, sir. Obviously, it comes under another person. That is, it comes under ED tools. So this is
Okay.
TCAD. What we discussed right now so far from the morning is completely TCAD.
Okay. Thank you.
Yes, thank you, sir. So any other questions we have?
Yeah, Dr. Purvasha.
Yes, please.
Can we take any one example very quickly from solar cells? So just we know how to run those applications also.
Okay, sure. Definitely. Just a second. Let me quickly take an example on solar cell. I'm just running it randomly. Okay. This is solar cell where it has been undergone a various fabrication step. Like you define the mesh in both X and Y axis. And initially you have the silicon, and then you give the boron and then orientation followed with the oxide coating, implantation. You perform various fabrication steps and you extract the junction depth, and then you go for an etching process, depositing aluminum, etching aluminum, and mirroring a structure, providing an electrode, saving the structure, and taking forward the structure to Atlas. That is, you call it as an in file, you call the same structure file for further characterization. So where you provide the material details. So this is solar cell. So you provide with this imaginary index file and Sopra. In this case, we have this user-defined specification file which can be included within the tool. It is beam solar spectrum specification. So we have this is a user-defined file which can be included with the syntax power.file. And then if you already have your Sopra database for the material that you're using, then directly you can incorporate it. But that is Sopra database, whichever universally available as a default is definitely available within Silvaco TCAD. And if in some case, which in some cases like it is not available, that is in default globally, then in that case, people go for taking the data collection, converting the columns, and that column file, that data file can be included within the device simulator and can be used for further simulations. You could see like if you want to see the optical intensity, then that's the reason I told. Like if you want to see any specific parameter from the device that you have created, you can use the output statement and visualize that particular parameter. Then defining the model, and then as usual going for the solve statement and loading the file. Here we have defined the beam. So we are going to like fix the beam with the value, and we are going to save the structure, and then we are going to solve the cathode electrode for the beam value of the specification what we have provided, and accordingly the structure can be saved and the plot can be viewed. The next is about the spectral response. So in this case, in the spectral response, you could see we have removed the specification, user-defined specification. It's a monochromatic light beam for spectral analysis. Beam with the number, which origin in the x-axis and which origin in the y-axis of the device it should fall, and which angle it should fall. So everything should be specified in the beam statement. So apart from that, all others are the same. So, and what we are going to extract, we are going to extract the efficiency, both internal and external, and then yeah, so this is what, and we just overlay the plot and we have a look. Let me quickly run this. I hope it doesn't take much time. So this would be, this is the structure, providing us with the photo generation rate. And yeah, So this is available photocurrent, available source photocurrent, and the cathode current plot with respect to the optical wavelength is being provided over here. And yeah, so the x-axis for the green one, it should be the source photocurrent, and the red one is available photocurrent. Okay, so I think it's done, it's completely done. So it has so many factors, so you can extract the power curve and efficiency, fill factor with respect to solar cells. So for extraction, you can definitely check the available examples. And if in case, if you are extracting a fill factor, so you can use, the syntax is going to be the same. So you can use the same syntax, extract it from what your curve, that is from the curve that you have simulated. So there are so many, you have the tantalum cell, you have the germanium cell, textured solar cell is there, organic solar cell is there, grain boundary, grain based is there. There are so many examples. Yes, 3D, but this is comes under Victory, so it doesn't comes under Atlas. So Victory is another suite, different suite.
Okay, actually, Purvasa, this is about one single cell. So if I say I want to make an array out of it, can I proceed with the same code with some modifications for making an array? I'm asking. Array of solar cells, right?
Yes, I got it. Yeah, this is one single device only. So in TCAD, we generally simulate one single device.
Right.
I can check and get back to you.
Okay, sure.
Yeah, I'll make this note. Any other question or any other simulation that you would like to have a look?
Yes, from participant side, please feel free to ask any queries. No. Purvasha, may I know one more thing? Do we have photodiodes optical measurements here, right?
Yes. TCAD supports photodiodes measurements. Yes.
Can we go through it? I just want to check some things, a few things there.
Oh, okay.
So any basic photodiode?
Yeah, let me just check because I don't know the file name. That's a problem. So 1 second, I'll quickly have a look. Okay, so this is an like cylindrical avalanche photodiode. So let me quickly simulate it, and it is using Atlas. Yeah, so it is a cylindrical type. So that's the reason we specify mesh cylindrical. Okay. So this is again X mesh, Y mesh, region specification, electrode specification, dopant specification, model specification. Impact cell is like when you go for a higher voltage, like when you go for understanding about the breakdown, all these and all, this impact cell will be called this particular Silvaco model. It is basically, so that will be called, and then method, and then we have different method to be included. Ramping, so you ramp from 0.1 to 1 volt, and then you're taking 70, that is 70 volt. So that's the reason we go for this impact self model, using this impact self model. And let me just quickly simulate.
Yeah, I'm interested in checking out with the source. How do we, where we are defining the intensity of the source, power of the source, and maybe the distance from the source for a sample, something like that.
Okay.
So
I don't know, this particular example is for, once again, let me just quickly have a check what it is. Okay, so it is with respect to Gigaboard, and yeah, it's for breakdown. Silvaco model is for breakdown, and then IV characteristic simulated using ramp voltage. Okay, so yeah, we have this electron avalanche probabilities. Cathode is ramped 70 volt. single electrons or holes at some points in the device. Okay. Let me just, I'll open it in the website mode because we can see what are all the plots that's been obtained. It is up to X19. I can simulate, but I don't know how far it will take. That's the reason I'm just selecting from the website. So this is without elimination. The breakdown characteristics. Yeah. And then under elimination. So, okay. This is a comparison of with and without. And then, yeah, including the jigger mode. So I think if any standard simulation paper is available for this particular example, I'll try to send you, so it will give you more details.
Yeah, please.
Yeah, I will just check, but I'm not pretty sure. Since if it is available, definitely I will send.
I hope you got my point. What exactly I want to ask, right?
Yeah. Yes.
Okay. Okay. Fine. So yes, from the participant sides, do we have anything to discuss? Please, you may come forward and ask.
Sir.
Okay.
And but anyway, so it was a long day for all of us, and to be frank, it's not very easy for a beginner to understand all these aspects in a day. Understanding a single tool in a full tool in a single day is very difficult. So I assume, and I am thinking that the participants or the students might need your support in future, so that you are able to, like, you have to address some basic queries associated with the simulation. Definitely. We hope that we would, or students would be reaching you maybe via the email that you have provided. So I will request that you kindly extend your support and help them out with the simulations in case whatever they want.
Undoubtedly, sir. Undoubtedly. So I'm just dropping the mail ID again in the chat box. Yeah. So I think participants can make note of it and